cement fail, I'm not saying. When I say, the structures start showing distress or deterioration in much shorter span than what we think of or what they are designed for. So, for example, there are statistics which shows, many 50% of the structures, they start showing distress and experience a repair in just about 10 years after construction or 10 years in service. And there are these distresses could be either due to the environmental loads or due to earthquake or other settlement, etc. So these are all problems which we need to start thinking about. And we have a large inventory of structures which are experiencing distress or which are going to experience. So coming up with a good repair strategies is very, very important. And when we talk about repair, it should not be cosmetic repair. It is structural repair is what we are talking about. And what we think is there are a lot of structures, which have been repaired and are experiencing, again, the repair itself starts failing in just another 5 to 10 years. Which is again costing more or leading to more economic burden to this country. So this topic is very important. I think the speakers are very well chosen to cover how to repair structures so that they can resist both environmental and mechanical loads which are coming onto the structures. I think with that I will stop. All the best for a wonderful program, and thank you very much for all the participants. Already I'm seeing 130 around participants. I think it'll be a great program. Thanks, Dr. Kannan, for organizing this, and thanks to all the speakers for agreeing to come forward. Thank you.
Thank you, sir. Thank you for your wonderful brief introduction. Successful and unsuccessful people do not vary greatly in their abilities. They vary in their desires to reach their potential. I take the honor to welcome Dr. P.T. Ravichandran, Head of the Department of Civil Engineering, to introduce our speaker, Dr. N.Subramanian, Consulting Engineer, USA.
Thank you, Ms. Pavitra. On behalf of the ICA Indian Concrete, Chennai Centre, and SR Institute of Science and Technology, and UltraTech Cement Limited, it's my immense pleasure to welcome as well as introduce one of the speaker, Dr. N.Subramanian, going to deliver the lecture on the topic case studies on failure, repair, and the rehabilitation of the structures. Our speaker had a brilliant academic career. He has passed out in UG from Madurai Kamaraj University in 1972 in civil engineering and postgraduate in structural engineering from College of Engineering, Guindy in 1974 and completed his research from IIT Madras. A former Alexander von Humboldt Fellow as a postdoctoral fellow at the University of Berlin and the University of Munchen in November 2020, he was selected as a fellow of the Indian National Academy of Engineering. Our speaker is awarded winning author, consultant, researcher, entrepreneur, and mentor. We have such eminent speaker on today to deliver the lecture. Our speaker dedicated his life mainly to the education and the enhancement of knowledge as the young British engineers and mentored them through his books, research papers, and also it is to be carried out through the social media and the lectures and through the leadership role in various professional organizations. Dr. N.Subramanian also written book, Computers and the Basic Language in Tamil, and also written a few Tamil articles which is published in Tamil Computers and Dinamani. He has also reviewed several books, papers for many reviewed and referred journals. He has received many awards on that. There are few, the Tamil Nadu Scientist Award, Gaurav Award from the Association of Consulting Engineers, Lifetime Achievement Award from the ICA, Best Book Award from the Association of Consulting Engineers India for 3 different books. In addition, as a Distinguished Alumni Award from the College of Engineering, India, Anna University, the Association of Society of Civil Engineers recognized his professional accomplishment. He is selected as a fellow in the year 2001 as a prestigious honor held fewer than 4% of the AAC members. And he is also a life fellow in 2015. In addition, he has played an active role in the Rotary movement as a social activities and served in several positions, including the president of the Rotary Club of Madras and also a district official. As a president of the club, he conducted several projects and got awards from the district. He visited more than 15 countries in addition to living in Germany for 2 years and living in the USA for the past 17 years. Recognizing his achievement, USA granted him green card and EBA, that is extraordinary ability classification. With this a small introduction, sir, again I welcome you on behalf of the ICA Chennai Centre, SR Institute of Science and Technology, and UltraTech Cement Limited, and on my own behalf. Thank you, sir.
Thank you so much, sir. I'm extremely privileged to welcome Dr. N.Subramanian, Consulting Engineer, Maryland, USA, to start the presentation.
Professor Radhakrishna Pillai, Professor Ravichandran, Professor Kannan Rajkumar, and other members of ICI and friends. First of all, good morning to all of you. It gives me a great pleasure to present first of all, I would like to thank Kannan Rajkumar for inviting me to present my lecture. As structural engineers, we always design using the codes. The codes are revised every 3 or 4 years. Of course, in India, the codes are revised after 20 years. But in most of the international codes are revised every 4 years. They are based on research conducted in different universities and research organizations, as well as due to the failure of structures. So I am going to present some of the failures of structures, though I have categorized them into failure due to failure of beams, columns, etc. Since given time is very much limited, I have added only 1 or 2 slides in each category. So with this introduction, I am just I will present my I will present my lecture.
Yes, yes, yes.
I am only showing some of the case studies of structural failures. So first, I will show one of the famous foundation failures. It is the Tower of Pisa. It is 56.4 meter tall, circular 8-story structure. It's a cathedral of the Italian city of Pisa. Actually, it began leading to southeast in the year 1173 due to 3-meter deep, poorly laid foundation and weak, unstable subsoil. Actually, 2 restoration efforts were taken, one in 1990 and the other in 2001. Before that, it lead 5.5 degrees. Now it is leading only 4 degrees. It was declared stable in 2008 and it is expected to stand for another 200 years. So more details can be seen from the 2 references I have listed below. Sorry. The next foundation failure is a very interesting failure in China. On June 27, 2009, an unoccupied 13-story block of building still under construction in China toppled over and ended up lying on its side. So you are seeing the structure on the ground. It is not standing. And 1 worker was killed due to this failure. It is from a paper presented by me in 2009. So the original building was on piles, and since they wanted to have an underground car parking, there was an excavation close to the building, and the soil was piled up at the back of the building, and due to this, there was overburden pressure. And when there was heavy rain, and due to this heavy rain, erosion started, and then there was an increased water table. And after considerable erosion, the structure started to lean, and then it fell on the ground. That is what you saw in the previous slide. So next we will see failure of columns. Of course, you know, most of you who are in Chennai know about the collapse of 11-story tower at Maulivakkam, Chennai. Actually, here you see the other building. So this was also removed due to safety concerns. It killed 61 people. Unfortunately, in India, we don't publish the causes of failure. Probably Professor Santakumar, who was in the committee, in his last lecture, he will explain more about this Maulivakkam failure. The causes are mostly gross deficiency in the design of RC columns. Some critical columns were removed for enlargement of the car park, substandard materials, and poor supervision of construction. The next collapse, which I am going to talk about, is the Sawar building collapse in Bangladesh. It is considered as the deadliest structural failure in modern human history. This happened in 2013. An 8-story commercial building collapsed in the capital of Bangladesh, killing 1,129 people and injuring 2,515 people. The causes of this failure, we will see. The building contained clothing factories, a bank, apartment, and several other shops. The shops and the bank at the lower floors were immediately closed after the cracks were discovered. Actually, this is a very important thing. Whenever you see large cracks, you should not allow people to go inside any building or bridges. Warning to avoid using the building after cracks appeared the day before has been ignored. The government workers were ordered to return the following day, and the building collapsed during the morning rush hour. The main cause of failure is probably because the upper 4 floors had been built without a permit. So this happens in India several times, and you have to be very careful. So even near my office, one building was constructed with 4 floors later. So I usually avoid that building. And during earthquakes, lot of buildings have failed due to open story for car park. This shows one building in Bhuj which collapsed, bringing the building down on its side. And next, we will go to failure of beams and slabs. This is a very interesting failure which was presented by D. Srinivasan, who was the Secretary General of ICI in 1975 in ICJ. Actually, this building was constructed in Neyveli. It had a span of 18 meters. As the bars were supplied at standard lengths of 12 meters, most of the rebars were lapped at the center of the beam where the failure occurred. So this happened in 1962. The beams in the central bay were reinforced with 738 diameter plus 120 mm diameter at bottom and 138 mm diameter plus 632 diameter bars at the top with a cross section of 1425 by 600 mm. The concrete was M15 because at that time M15 was allowed. During the removal of shuttering on 26 January 1962, the entire roof caved in along the ridge. It is because all the bars were lapped at the same point. Of course, failure of slabs are rare, especially in small buildings, but in high-rise buildings, especially using flat slab, you have to be very careful to support them properly. This is a failure which happened in Virginia, USA. This 30-story cast-in-place RC flat slab structure under construction resulted in the progressive collapse on March 1973 due to punching shear on the 23rd floor. And it resulted in the death of 14 construction workers and the injury of 34 people. All floor slabs are 200 mm thick. The lessons learned from this particular failure. Is that redundancy is essential to prevent progressive collapse. Construction loads, which will govern the design, must always be estimated and considered in the design. Concrete casting, formwork plans, removal of formwork schedules, or reshoring should be decided in consultation with the contractor. Before the removal of shoring, the concrete strength should be ascertained. Proper shoring of the currently executed floors below should be verified, especially in flat plate systems. Due to this failure, ACA 318 included a provision to place rebar continuously through the slab column joint at the top and bottom of slabs. If the slab fails in punching shear, the bottom bars can act as catenary and prevent the collapse of the slab. Of course, several other flat slab structures have failed due to punching shear. I have listed some of them here. Those include one building in Florida and one in Ontario, Canada, and Seoul, Korea, and UK, Switzerland, Italy, and so on. Several systems failed during earthquake. That is why our codes do not allow flat plate system without any other lateral load resisting system in earthquake zones. The next failure, which I am going to show, is the Berkman Plaza, Jacksonville, Florida. This occurred in 2007, and 60% of the structure collapsed suddenly like a stack of pancakes, killing one and injuring 23 others. It had cast in place simple RC columns, cast in place RC and post-tension concrete beams, and cast in place post-tension concrete slabs. The cause of this failure is due to errors made in design, construction, and inspection. The design had numerous deficiencies as per formwork plan shoring and reshoring to extend all the way to the ground. But shoring and reshoring below the third level had been removed shortly before the concrete on the 6th floor was placed. The next one is I am going to show is the progressive collapse of Ronan Point building. This is a very interesting failure which resulted in code changes. Actually, the progressive collapse provisions were introduced in the British code and also in other codes in the 1970s as a result of this failure. This is a 23-story tower in East London. It suffered a partial collapse when a gas explosion demolished a load-bearing wall, causing the collapse of one entire corner of the building, which you see here. 4 people were killed and 17 were injured. Actually, I think I have removed some of the slides due to terrorist attacks. So as a result of terror attacks on embassies abroad and Murrah Federal Building in Oklahoma City, abnormal loads were introduced in the US codes. And I think in the 5th revision of IS 456, structural integrity requirements are also being introduced. I have discussed this already. So bridge failures, several bridge failures occur. I think from one of the papers I read, I see that bridge failures are in India as well as abroad. So I am showing. I-35 bridge over the Mississippi River in Minnesota. This one collapsed suddenly in 2007, killing 13 people and injuring 145. As per the reports published by the National Transportation Safety Board, These are the following. These are the causes of the failure. Under design gusset plates, it was a major factor. And after this gusset plate design, several papers appeared in the AISC for the design of gusset plates, and weights added to the bridge over the years. Actually, 191 tons of construction material was piled over the bridge at the time of failure. So next I am going to show window-induced failures. Of course, this is a very famous failure which many of you know. It occurred in 1940. It's a Tacoma Narrows Bridge. This bridge had a total length of 1,810.2 meters and a central span of 853.4 meters, and collapsed in November 1940 due to the twisting of the bridge deck in mild winds of about 64 kilometers per hour. This failure was by torsional vibration mode caused by aeroelastic fluttering. It boosted research in the field of bridge aerodynamics, which resulted in better bridge designs. This is another interesting failure of cooling towers at Ferry Bridge, UK. Three 115-meter tall hyperbolic cooling towers failed by, these are the three towers which failed through snap-through buckling at England in 1965 due to vibrations in 137 kilometers per hour winds. The main cause were the average wind speed over 1 minute period was used in the design, whereas the structure were susceptible to much shorter gusts, which were not considered in the original design. Actually, the designers used wind loading based on experiments using a single isolated tower. But in reality, you see 8 towers are placed close by. The shape and arrangement of this closing tower created turbulence and vortex on the levered towers that closed. Similar failures resulted in the revision of building codes all over the world to include provisions regarding improved structural support and necessity of doing wind tunnel tests for complicated configurations and arrangements. So next 2 slides are actually are steel structures, but just I want to show that detailing errors can cause catastrophic errors. So this is a structure which failed in Kansas City, Missouri. This is a 2-story walkway, 2 overhead walkways in the hotel loaded with party goers crashing onto a dance floor in the lobby, killing 114 and injuring 216. You see that there are 2 floors of walkways. This is the top one, and at the bottom was the second one. And it was connected by a single rod with a nut. But the actual construction was made by using 2 tension rods. One is from connecting to the top and one connecting to the bottom. Due to this, there was a lot of twisting and the structure failed. So the change in the design was not approved by the designer. And this is another important roof collapse. It happened in the 70s. Fortunately, no one was killed because of the early morning failure of this structure. Only 6 hours earlier, 5,000 people were watching basketball. It was a large 90 by 110 meters space frame. Actually, during construction in 72 and 73, the inspection agency notified the engineers of excessive reflections. Measured deflections were twice that of predicted by the computer analysis. So this failure shows that computer analysis itself is not sufficient. You got to be very careful to study the behavior of the structure before designing them. The main cause was the top parts had much lower buckling capacity than assumed in the design. The unbraced length of some compression members were 9.14 meters, whereas in the computer analysis, it was assumed as 4.57 meters. Thus, the capacity was reduced 75% by this factor alone. So I wanted to show some of the recent failures. This is a collapse of pedestrian bridge at Florida International University in 2018. It collapsed at about 1:46 p.m., crushing 8 vehicles, killing 6 and injuring 10 people. The causes of the collapse are combination of design errors, inadequate peer review of the design, poor engineering judgment, and response to the cracking that occurred in the joint region, which led to eventual failure. The lack of redundancy caused the bridge to collapse. Actually, when there were cracks, the people in charge of the bridge at the site, they never bothered because it's a pre-stressed bridge. They thought that by pre-stressing, the cracks will disappear. Actually, there was a truss. So from the previous photo, it may not be clear, but there was a truss. And number 11 and 12 of the deck were connected via a cold construction joint. The surface of the cold joint was assumed to be roughened to an amplitude of 6.35 millimeter, and the coefficient of friction was assumed as per ACA 318/2019 as 1. But after the collapse, the designers found that the contractor did not roughen the cold joint at all. Of course, this is one of the causes of the failure, and there were recently you might have heard about this Champlain Towers, Miami. It was built in 1981. The 13th floor flat slab building collapsed suddenly on June 24, 2021, after 40 years, killing 98 people. And official cause of the failure is not yet known, but there is a investigation going on, which will be publicized later on. But I feel that the failure is due to corrosion of rebars, due to improper maintenance, punching of flat slab due to this, and column failure due to corrosion may be the cause of failure. And the final case study, which I am going to show, once again of the first slide I showed about the foundation failure. I am closing it with another foundation failure. Actually, it has not yet failed, but it has sunk. It was opened in 2009. It consists of 12-story tower and a 48-story, 197 meter tall Millennium Tower. Of course, the sinking happened only in the Millennium Tower. In 2016, the tower sank 41 centimeter with a 5.1 centimeter tilt at the base and 15 centimeter tilt at the top, and caused cracks in the basements and the pavement surrounding the tower. In 2018, the sinking increased to 46 centimeter with a lean of 36 centimeter. Actually, you see that initially they provided piles, friction piles only. They did not go up to the bedrock. But now they suggested an underpinning solution, which consisted of 52 members, 76.2 meter piles along the north and west sides of up to the bedrock. They estimated that about 50% of the tilt will be evened out over a period of 10 years. This is a 100 million repair of perimeter pile upgrade. It started in 2020 and it was stopped in 2021 as there was additional sinking of 25 millimeter after 39 of the 52 piles were installed. I don't know what will happen, but a lot of people have sued the developers. It may be interesting to note that providing this bedrock, the piles up to the bedrock costed only $4 million, but already they have spent about $250 million for the repair. Finally, I just wanted to show this is a paper of a, sorry. This is a paper published in 2003 for the analysis of recent bridge failures in the United States. You will see that initially the design was the main cause of failure, but which has reduced to 3%, and also the distress also, which has reduced considerably due to design. But now the failures is either due to construction or due to external factors. So in summary, several failures of RC and steel structures are happening throughout the world at regular intervals, and the failures may be due to problems in foundation, columns, beams, slabs, walls, or due to wind, earthquakes, or severe loading. Though design errors are rare, as I told you in the last slide, many errors are due to detailing, execution, corrosion, or improper maintenance and poor materials. It is important for structural engineers to study these collapses, find out the causes, and avoid these mistakes in their own practice. Unfortunately, in India, the cause of failures are not made known. It is also important to have peer review of design, especially for special buildings or very large buildings. And it is very important to have coordination between the parties involved in the construction. That is, designers, builders, and architects should coordinate and clearly explain the concepts. Computers should not, results should not be blindly accepted, and maintenance is as important as construction. I think this is his last slide. I thank you once again for your patient hearing.
Thank you so much, sir. Thank you for sharing the knowledge on various case studies from international experts to cater the engineering community. It was a great insight on progressive collapse failure. The forum is open for questionnaire session. The participants can unmute and can ask the question.
Vitra, may I ask one question?
Yes, sir, sure, sir.
Dr. Subramanian, thank you very much for this talk. Like your second bullet on the screen says, unfortunately in India, the causes of failures are not made known.
Yes.
In fact, I was going to ask you that question and comment on that. Then you yourself put that bullet. Sir, what can or what we should do, as a country to change this, because that's, I think, the most important thing which we have to do, right? Give that, what is that we have to do? Because this fear of fault finding is everywhere. What we should do to avoid that fear?
Actually, in India, we are, especially even for that failure in Chennai, which I showed, there was a committee, and they found out the causes, but it was not published. So I don't know why. Whereas in the USA, every failure is investigated and the results are published. So people will know, and people will not repeat that failure in their designs. So it actually, even for that Florida failure, the investigation is going on, and I'm sure that it will be published so that people will not repeat that failure in that practice. I don't know why in India it is not being observed.
Yeah. Okay, sir. So this is something which we can talk for long. So maybe.
But I think IIT recently published the results of that Gudse buildings.
Which one?
The
Slum clearance board, sir.
That 20,000.
Yeah. But that, yeah.
I saw in newspaper recently.
Yeah. But it's only again in newspaper. It's not coming into the
No, at least in newspapers it is coming. But many failures are not. They are reported once the failure occurs, and after that there is no reporting.
I think we need a cultural change is probably required.
Yeah. And some of the things are also political.
Okay,
Even
sir,
one building in Bengaluru which failed recently. It was a G+4 building. It just tilted on one side and it was failed.
You saw that video?
Yes, sir.
Right. Actually, I don't know. Probably it was due to corrosion.
That's exactly, we don't know. We don't know the problem. And nobody will tell us. If we call, then they will, Yeah, we need to probably change this culture of, hiding the data or hiding information rather than.
Data should be made available.
Yes.
Thank you, sir.
So any other questions, sir?
Any other questions from the participants?
Sir, can you just highlight what is the reason behind the Tacoma bridge failure? How they remodify the bridge further?
This Florida bridge.
It's 1946.
Tacoma.
Yes, yes,
Actually, there was the beams below the bridge were very solid, and due to this wind on the structure was more, and it resulted in twisting of the bridge. So after that, several bridges have been the same place. Bridge was built, which a lighter open cross section towers. Trusses.
Okay, sir. Thank you, sir.
Thank you, sir. I am extremely privileged to welcome Engineer Ganapathy Ramasamy to introduce our speaker, Dr. V.Rajendran, Managing Director, Hitech Civil Engineering Services Private Limited.
The screen is visible to you now.
Yes, screen is visible.
So it is my immense pleasure to introduce Dr. V.Rajendran, Managing Director, Hitech Civil Engineering Services. So he is working as a visiting associate professor in various colleges like Meenakshi Engineering College, P.S. Abdul Rahman Crescent University, GMR Institute of Technology, Vizag. And Rajendran sir has done a lot of practical applications. Few of the examples are given below. That is retrofitting of roller mill beams and columns with CFRP plates and seat wrapping at Corrosion cement plant, Sri Lanka for Humboldt. Repair and rehabilitation of Saraswati Hostel building, phase 1 and phase 2 for additional seismic forces due to addition of one more floor at IIT Madras. Modification or rehabilitation of the corroded piles and pile cap at Finger Jetty at erstwhile Chogani floating dry dock in Chennai Port Trust. Rehabilitation of culvert beneath runway chainage at CA Hyderabad. Cathodic protection for the corrosion affected jetty at Visionary Marine Terminal at Port Sudan. So these are some of the examples of the practical applications. He is a life member of various professional bodies such as Indian chapter of ACI, Indian Concrete Institute, American Society of Technical Education, Institution of Engineers, Association of Consulting Civil Engineers. He is a secretary of Rotary Club of Alandur for the period of 2019-20. He is a secretary of Association of Consulting Civil Engineers, Chennai for the period of 2019-20. He has received Eminent Engineer Award for the year 2018 from ACCE India. He has published more than 240 papers in national, international journals, conferences, seminars, workshops. With this small introduction, I am very happy to introduce that our sir, Rajendran sir. We welcome you, sir.
Thank you, sir. Can you close the screen and then make me a co-host?
So you already co-host, sir. Ganapathy can stop the screen share.
Yeah.
I did.
The screen is visible, sir?
Yes, sir.
Yeah. Good morning, one and all. And first of all, I thank Professor Kannan Rajkumar for giving this opportunity. And special thanks to Radhakrishna Pillai sir, and then Ravichandran, head of the department, SRM, and also to UltraTech. This case study is going to be a single case study where we have involved, including design and execution of this. This is a desalination plant which is done at one of the islands in Lakshadweep. where there was a design error, in the sense not exactly straightforward design error, but of course, the sequence of construction was not taken into account while the design or the modeling was done in computer. And probably this, I think I already, presented this in some of the forums. I'm not sure that it has been done for ICI. Well, as NSR said, there are many causes for failure. There is no single cause which could be explained, and especially in India, as he was rightly pointing out, that even this recent result on this care complex where you're talking about the slum clearance board, we've been keep talking only about, the report was keep talking only about the plastering, but doesn't have any say about the structural elements like columns and beams. So there is no single cause of it. This particular case study which I'm going to talk about, although there are many other causes for distress, which can be material quality or construction deficiency or durability due on account of corrosion and so many other things. I'm just confining this particular case study only to the design deficiency, where the underestimation of loads and shears and moments have taken place in this particular case study. Now, coming back to this case study, as I said, it is one of the island at Lakshadweep, where we know this, where we know that this Arabian Sea used to be very shallow for a long distance, and then suddenly it goes too deep, which is very conducive for us to have this low thermal temperature difference based desalination plants. What we try to do over here is that we have, as for the civil part is concerned, we'll be having a floating foundation till it is embedded into the, or erected into the seabed, and you will have a sump which is a watertight compartment to house two powerful motors. One motor will be drawing water from the surface of the sea. The other would go about 800 meters to 1 kilometer below, so that the temperature of the sea water will be very low when comparable to the surface water. Both these will be brought to the plant, and you will have a flash chamber and a condenser, and both the warm water and cold water sent to the flash chamber and condenser, where the condensation would take place, and then you collect the condensed water as a good drinking water, and then which comes to the shore. Now, this is what the whole construction. What we need to do is that we need to have a sump. Only thing is you cannot do it. You cannot do any construction outside, because these islands are with a lot of live corals, so environmental clearance would not be given. All that what you need to do is that you need to do all your construction activities on shore, float it, bring it out to that particular place, and then anchor it into the seabed. So when you wanted to float it, then you will not be able to take the structure complete construction also, for the simple reason, the buoyancy will not be available, the depth of water, and especially when you wanted to bring it to the mouth of the jetty will be very low. So it will be done in 2 or 3 phase construction, and then it is floated and then taken, placed into that sea. So mostly all that partially precast and then float it, bring it, and continue the construction. That's a system which was adopted. And another biggest constraint is that these islands, very, very small islands, and then does not have any infrastructure facilities like, crane and things like that, except, few cranes which is being handled by this Lakshadweep harbor works. As the population is very low, there is no industrial or any other growth. Things are, only based on fishing and then coconut tree growing. Even drinking water will not be available, because the, digging a well is prohibited over there. And we need to take it either from Calicut or from Kochi for doing the construction activities for this sump and then bridges. This is levels at which I'll show you why this, there is a steep slope in this. That's all the failure about this P11 pile all about it. And then that's what made us to go for a different level in this particular site, is not at the same level. This is a finished one, and where we are going to talk about is this particular pier which has failed. As I was explaining, the temperature surface water will be about 28 to 30 degrees. As you go, you get about 17 to 15. The warm water is flashed inside the vacuum flash chamber, and the resultant vapor is condensed using the cold water. If you look at the quantum, for getting 1 liter of drinking water, somewhere around about 400 to 450 liters of seawater is being drawn, and then in the 600 millimeter diameter pipe. When it is sent back, it is being proposed to send with the 230 millimeter diameter pipe, so that you will have a captive power plant which will produce electricity, so that the entire project is self-sustained. The biggest advantage over here is there is no chemical in addition for taking this, drinking water, or it's not the reverse osmosis system where you need to keep changing the, membrane very frequently. It is completely self-sustainable project all about it. In the condition of environmental has been studied, proximity of 5-meter depth contour was there on the shore for taking the intake structure, and 400-meter deep contour from the shore to intake the water, where you get a temperature about 10 degrees to 12 degrees. It was done during April, May. You will have 35 degrees surface water with the humidity of 70 to 75%, and average wind speed is about 5 to 6 meters per second, the maximum of 39 meters per second during the monsoon. And the wave load what has been taken for this particular design is about 200 kilonewton per square meter, and the wave height was maximum about 5 meters in the pre-monsoon and 9 meters during the monsoon. These are the data has been collected for the design aspect of it. The dimensions of the sump, if you look at it, the floating, the foundation which you are going to make at the bottom is going to be about 12.17 meter by 8.3 by 9.1. Because as I said, during peak monsoon, you'll have about 9 meters of wave height, and then pre-monsoon you'll have 5 meters. So 9.1 is what we have been designed for the sump, foundation. And over which you will have 2 compartmental, sump, which will be watertight, of course, so that, it will have 2 electrical motors for drawing the water, which is actually a intake structure. Otherwise, if you don't call it as a sump. The design, what has been taken into account is dead load, live load, equipment load, direction load, wing load, hydrostatic and load combination as per 4651. All the loads have been taken, and 200 kilometer per square meter was the wave load which was taken, and which was also tested for overturning and then slide, because the sump is going to be anchored only at one end, and it is going to be like a cantilever retaining wall sort of a thing. So overturning was checked, and then sliding was checked, and all as per the design calculations. Now let me go to the pictures and cite what happened. This is an aerial view of the island, and initially what we did is we did the bathymetric survey to find out which is going to be the maximum depth by which we'll be able to take out the sump in through the mouth of the island, bring it to the other side where you'll have got a fisheries harbor jetty is already available, so that you can tie it to the partial construction and continue the balance of it. As we all know that the bottom of the sea will not be is not going to be the plain one. It's going to have a lot of undulation. So the permission has been given for 15 meter by 15 meter, where you'll be able to make the surface of the seabed fairly leveled enough. If not, it's going to be exactly. And also we have proposed to go with a pipe on the raft foundation, so that once the sump or the floating structure is anchored into the seabed to a depth of about 12 meters through a 32 millimeter diameter anchor rod used with polyester resin which sets underwater. We also wanted to grout this base of the raft after the construction and the seabed with the non-shrink underwater grout. So for that, the maximum possible extent, the chipping was done, so that we don't have any point load which is coming onto the raft design, because it is taken as an UDL. I'll just go. There's nothing to show about it. Now, construction on shore, as we see, we have done the bathymetric survey already. Based on the survey, we have taken the weight to what extent we'll be able to float. We got about 200 tonner can be the load which can float, the other side of the island before you bring it to the mouth of the island. So we have gone up to 3.5 meter, and you can find all these inserts have been provided for the pipelines to get connected. As I said, it's about 3.5 meter, although 200 tonner is a buoyancy which can float. We have taken about 170 tonner is the weight of this at this particular point. And as I explained already, although we are going to make the seabed to a fairly level surface, but we will not be able to make it pakka. So what we did is, when we casted this raft, we have provided a PVC pipe in about 18 numbers, so that we'll be pouring this non-shrink free flow grout which sets underwater after making the barrigation underneath the seabed at 9.1 meter, so that this grout does not flow. And as this grout has got a property of non-shrink, it expands and then it makes a perfect contact between bottom of the raft and the seabed. That's like any other slip form arrangement, has been done. Slippy arrangement was made, which is being normally done in the harbor, where you'll be able to push this into the water and it will float and you'll be able to bring it out the mouth of the sea. So, we, in addition to the pushing, we also wanted to pull it. You can find, your anchors have been placed where the sump is there in the shore, but anchors have been placed over here. Simultaneously, both pushing and pulling has been done, and 200-tonner jacks have been used to push this sump into the water during the low tide level, so that your steel frame arrangement for the slipway can be monitored properly, whether the underneath support is being placed in position, whether it is moving or first step. So this is during the low tide level, and once you get the high tide level, it starts floating, and then you just bring it out through the mouth of the island and bring it to the fisheries harbor jetty, which has been already there, which is being used by the Lakshadweep Harbor Works. And the further constructions have been done, and later on, taking this and then putting in the position, we'll be filling this proposed with the pig and O, or otherwise with the blue metal of 40 mm, so that the dead weight calculation goes as per the design calculations. Actually, this is what the structure we would like to have it functionally for using this. We are used in a completely Tata CRST. I would like to pass on this one information, that although we bought this corrosion resistant steel well before the steel was even used, we found that when it was there on the shore itself, despite as a CRS, we found number of rods got corroded in the shore itself well before it was put into use. So we thought that CRS is going to be a foolproof system where nothing is going to happen, and that was not the case. After that, this was taken, and the entire structure has been taken out when it comes to the open sea with a further construction, which was floated, and it took about 4 nights and 5 days for us to bring the structure to the other side of the island, so that where you will be able to anchor this, and the proposed bridge structure and the plant structure is being done. The challenges over here is coal joint. We don't want any coal joint leaking to be taking place, so we have used both type B and then type B waterproofing system, because type A we will not be able to go as per BS 8102 or 2009, and where we use these water stoppers, both PVC and also expandable water stopper, swellable water stopper, and we have used this admixtures, where we have got about 6 hours slump retention, and then we avoided to the best possible system of your coal joint, so that it doesn't leak and then get into it. So this was floated and then brought to the particular place where it is supposed to be anchored, and the anchoring was over as we discussed. And this is your structure which is going to come under the wave breaking zone or a bit earlier to that. Now you can find this particular area is what you're going to have much of issue, where this wave breaking zone is coming. The maximum force is going to be over there. As I said, even the foundations also will not be able to do the cast institute foundation. It has been isolated foundations that have been designed originally, and it is casted at site, and then we have taken that and positioned it. Especially in the wave breaking zone, it was not a single isolated footing, and partial of this has been done, and this was also floated. Now the problem is, at least the sump, you'll be able to bring it through the mouth of the island. Where it comes to the open sea, the buoyancy is not an issue at all. But whereas in this case, the depth is going to be very low. So you make additional, you need to provide additional buoyancy effort. So we made the same shuttering formwork system like this all around, and provided the sealant in the joint so that no water gets percolated. And in addition to that, we also used pipes for getting the additional buoyancy force. And once it is done and made perfect, then the partial concreting was done. You can find this for additional buoyancy. We also tie these tubes so that it can flow without any issue. Then the same way how the sump structure has been floated, and this was also taken. And you can find the sump has been already anchored into the seabed. Now for the bridge structure, you need to align this and then position it and anchor it. I'll just run this alone. The line and length was not a problem because we were able to achieve it with all this, 4 levels. We had tied it and then brought down to the perfect position. If it is not, sinking into the perfect line and length, we will have a problem because the top girders which are coming, the concrete girders or precast girders, we don't have, much of play on that, so that, it has to be positioned in a proper manner. The whole issue is a lot of constraints over there. Now you can find the length, size, line is not an issue. It is perfectly, on the line which is expected. The problem what we faced for, which has, made us, pushed us into rehabilitation or retrofitting, was this, P12, pier. And as I told you, there were precast beams, and after that, this precast beams will be placed on top of these columns, and then it will be concreted with the micro concrete, so that you don't have no issue as far as the congested reinforcement is concerned. And we use this A-frame, which is normally used for girders launching from one pier to the other pier, and deck slab casting has been done. This is a modeling of the plant structure. This is a plant structure which is under construction. Here we don't have much of issues because it's not under the wave breaking zone. And once everything is over, and this is a high tide level, and we found after we removed these steel sheets all around it, and then we wanted to go with the further construction of this column height to match the level of your girder. We found that during the monsoon, heavy forces were there, but of course this was already taken into design consideration. But we went underneath. We found that there's a crack which is taking place in the 2 columns of your foundation, which is started slightly, first as a crack and started leaning, and then the crack which was widening, and then concrete started falling, and you can find that it started leaning towards this, and one point in time it has already come and touched the other 2 columns, where if you found at the bottom, you can find absolutely there is no concrete, that the raft and the column join. And then after these columns are touching the other 2 columns, once the moment is over, then we have shear into effect. These bars of 20 millimeter diameter bar, 4 numbers, got completely cut as if it was cut with a cutting machine or with a hacksaw frame, and all these ties are not in position, and this is what happened. And again and again we started redoing this revisiting the STAD modeling, and then modeling was done perfectly, and there is no issue. There was no error. Everything was done, and then design check was done. In fact, we have given we also involved IIT, so that as a proof check, and proof check was done, and everything was in line. But finally, we had this issue in the site. This was the failure which has taken place. Now, how it was rectified? That's what. Now, what we did is we need to first bring back the column into the position and go to the underneath underwater. Use the hydraulic drilling equipment, where you'll be able to make holes into the raft, and then provide additional reinforcement and put formwork and make the underwater epoxy concrete, so that you'll be able to set both underwater and be able to take care of your expected moments and then loads. It's very simple. I mean, like what we do on the shore, the same thing has been done over the foundation at the raft, about 9.8 meters to 10 meters roughly from the sea level. And after that, there's a reinforcement detailing of this gauge which has been placed, and then the formwork have been made, and we were able to do this underwater epoxy concrete, and it was done. Now again, the problem is, although you do the underwater epoxy concrete, we will not be able to wait for the girders to come and then place it. So what we did this time, we don't want to take chance. No sooner the column has been brought to the particular level which we needed for the bridge, we made a steel girder ready before the rehabilitation works started, because even to take this underwater epoxy concrete, it took about 45 days for us from Calcutta to the site, because that was an issue over there. Logistics is the biggest problem. and then reaching the site is another issue. In fact, even for working team to go, you need to get the permit and then reach. Although it is a part and parcel of India, we will not be able to go just like that. So what we did is, we had taken additional steel from Calicut, and then we made this steel girder assembled. The moment the column has come to that level, and the steel girder was placed up in position, and the deck slab concreting was done. Actually, what went wrong was over here is that we are not taken sincerely the sequence of operation which is going to take place in terms of load which is going to come and act on the structure well before the girder was placed. As we all know, in the modeling, we make all the members connected together. For example, column, and then you connect the beam, and then slab. Everything is being connected, like the member parallel to x-axis, parallel to y-axis. All that is getting connected, and finally we go to the command of application of load. And once you do the application of load, and then you do the process the analysis, and then take out your salient features of your bending moment, or shape, or whatever it is, and then we do for the design. But here what happened is, well before the girder was placed right over the column, the complete load started acting on these columns, wherein the column where what was considered in the modeling for both ends are fixed, whereas when the load was applied, the full load was applied during the monsoon, one end was fixed, the other end was completely free. The end condition was not that same what we adopted while we made this modeling, which made a complete failure. The lesson what we learned, normally in prefab structures, we used to say that handling stresses are always much more than the actual stresses. But in this case, the sequence of construction was not taken into account, which made us, to shell out maybe about another 50-55 lakhs in addition to the original construction cost, and then prolong the project duration by about 48 days because of this particular failure. So this was a design failure which has taken place where that was not taken into account. So probably as designer, we definitely need to, as NSS said very rightly, all the stakeholders should be brought at the design stage itself. Okay, this is a design I'm giving, but how is that you are going to construct? How is it you are planning to execute it? Which will make us clear so that you will be able to adopt an appropriate end condition, which would have not costed this failure, and we would have not wasted time and money. This is a case study I thought that I should share. If there are any questions, I'd be happy to answer.
Thank you so much, sir. The question is open. The forum is open for questionnaire session. The participants can unmute and shoot the questions.
Good morning, sir. Can I ask my question?
Yeah.
Sir, could you just repeat that point about how the sequence of construction played a role in the failure of the column? Could you just repeat that part?
Yeah.
Thank you.
As far as the beams are girders are concerned, it's all precast on the shore. As I said, we will not be able to do in-situ construction over that particular area because the live corals are there. Environmental clearance could not be obtained. So you have to cast your footing and then float it, and you have to anchor it. When you look at the StatPro modeling, normally what we do, we take the the first footing first, and then you have the whatever the end condition, your support condition you are going to give, you are going to give it, and then your column, which is along the y-axis, you are going to take it, and then you take the beams along the x-axis, and then you are going to place it on top of it, and then if you wanted to go number of floors, you do the mirroring, and also you go with a slab or whatever that, if it is going to be a deck slab. Once every modeling is over, then you are going to apply the load. But here in the construction, what happened, when we wanted to bring the girder, it takes about a week's time to 10 days for placing the girder over this column. Before that itself, the entire load is coming and acting onto the column, which is having a end condition of one end is fixed and other end is free. Whereas in the modeling, it is not one end is fixed and one other end is free. When the load was applied, both the ends are fixed. That has made this failure in this.
Got it, sir. Thank you. Thank you.
Welcome.
So just one more thing for
Yeah,
underwater construction. I mean, how I mean, except besides the concrete cover, what are the other ways that we can delay the corrosion in the reinforcement? I mean, corrosion is something that cannot be avoided completely. It has to happen someday or the other. But for underwater, where in environments with high chloride presence, how can we delay the corrosion process?
Yeah, Professor Pillai sir is here in this forum, but still what we do in industry practice is that one is that cover 70 mm, whatever the quarter provision we follow. And as I said that we have adopted CRS steel over here, but it didn't work for us because we were able to witness the CRS steels are getting corroded right on the shore, which was placed well before it was used for the construction. But what presently we are using is that we are using the we are providing the sacrificial anodes, the self-sacrificial anodes based on the steel density ratio. We tie these anodes to the rebar. Eventually, the corrosion is going to take place. As you rightly said, it is going to have too much of chloride, and the environment is completely surrounded with chloride, and also especially in the tidal zone difference where you are going to have this wetting and drying process is going to take place continuously, which is a very conducive atmosphere corrosion. What we are trying to do is that by providing this self-sacrificial anode, we are trying to shift this corrosion from the steel to this anode, because basically these anodes house zinc into that, and then the zinc gets oxidized and go as a zinc oxide. Thereby your steel is left as it is intact. Probably you may have to use 20 years once you may have to replace the anodes. That depends upon your steel quantity, what has been used, and then the rate of corrosion. That's what at present we are doing.
Okay, thank you, sir.
Welcome.
Is there any other questions from the participants? If you have any questions, you can directly mail to sir. Yes.
Yes, sir. Go ahead, sir.
Proceed, please.
Madam, you can continue, madam.
Yeah, okay, sir. Thank you so much, Rajendran, sir. Thank you for bringing an insight to investigate failed and damaged structures, especially in the underwater, which is a very challenging task. Thank you so much, sir.
Welcome.
Sir, can I unshare, sir?
Okay.
Screen, sir.
Yeah, that's it. Yeah, done.
Thank you, sir.
Should I proceed, sir?
Right, madam, we can share the screen, madam.
Yes, sir. So just give me a moment, sir.
Shall I share, madam?
Yes, sir. Yes, sir. No, sir. I'll share it, sir. No issues. I take a great privilege to welcome Er.Dhruvesh Shah, Head India Business, MS Vector Corrosion Technologies, Canada in India. Er.Dhruvesh Shah obtained his ME in Structural Engineering from MS University Vadodara in 1995. He is involved with the health study and corrosion assessment and execution of various civil engineering projects in the specialized field of corrosion mitigation, repair and strengthening of RCC structures in diversified industries since last 25 years in India and UAE. He is one of the faculty in CII's Corrosion Manager course for developing corrosion managers and board members of CII's Corrosion Management Committee. Our speaker has delivered various presentations and published technical papers in FICCI, NAC, COR-Con and ReadyCon and NIGS SZ at IIT Madras, IIT Bhubaneswar and various private universities. Currently, he is Head India Business for MS Vector Corrosion Technologies, Canada in India, and consultant for corrosion mitigation and strengthening of RCC structures. Recently, he has published an article in Journal of Building Engineering on the title Long-Term Performance and Life Cycle Cost Benefits of Cathodic Protection of Concrete Structures using galvanic anodes along with other researchers. We welcome you, sir.
Thank you. I will share my screen.
Yes, sir. Yes, sir. You can proceed.
Is it visible now?
Yes, sir. It's visible.
Yes, sir.
Yeah. Good morning, rather good afternoon, everybody. And it's happy Diwali to all of you in advance. And hope this festival of light and enlighten all of our lives after the grief 2 years of COVID, and it merges with the enlightenment of civil engineers, basically with all the fraternities, sections of ICI, Chennai and Department of Civil Engineering, SRM University. If it can enlighten all the people, and if everybody can have at least one failure avoided, or they can use with the help of this case study and this webinar, if we can have one structure made good, rightly, correctly, then it will be a great achievement for this webinar. So I hope that all of the participants, around 250 odd participants, and if we are able to share, like save 250 structures rightly and have a good repair practice or good strengthening practice, it will be a great achievement. And we wish that such type of webinars happens every now and then. Now to start with my presentation, like outline, it is a brief introduction, failures in RCC structures and solutions with lot of case studies. Just to introduce brief, like vector corrosion technology is a world leader in corrosion mitigation solution of RCC structures, having various galva shield, sacrificial and other type of anodes, and they have offices all over the world, head office in Canada, and take care of business. As I said, I take care of vector business in India, and we have two distributors, one in Ahmedabad and one in Chennai. Dr. Rajendran is one of our distributors. He is a helping hand. And regarding failure of structures, I will not take much time in, as our earlier speakers had shared a lot of things about the failures with wonderful case studies. Basically, they can be natural calamity, design and construction stage, environmental stage, and man-made changes in the use, or you can say abuse of the structure, which causes failures. And if we term in technical terms, it can be a structural failure and durability failures. And these durability failures lead to a structural failures. And structural failures can be a compression failure, flexure, shear, punching shear, or deflection. But I will talk more about the durability parameters, which, like, because of the leakages, there is a problem with the structure and corrosion. This corrosion induces cracks and spalls in the structure, and then it further reduces the load carrying capacity of the structure, and it leads to a structural failure in various forms. So corrosion, what rightly other attendee has asked to Dr. Rajendran that what to do for the corrosion of rebar in underwater. I will take care of how to take care of corrosion in case of environmentally exposed condition. Just to go in detail it with other case studies to understand all these people, I will have one small corrosion cell in the, one slide for the corrosion cell in the concrete. Like this is a simple concrete where the two steels are tied and the rebar is having a good passivating layer because of the high pH of the fresh concrete. And when there is a contamination in the form of chloride, by what you have prominently in Chennai, the chloride ingress may be due to diffusion or various other ways which I don't want to go right now. And this, when chloride ingress, it reduces the passivating layer, and in presence of oxygen and water, which is quite possible in having high humidity, and the steel which is in vicinity of the contamination will become anode, which will corrode, and the steel which is away from the anode or is not in vicinity of the contamination will become cathode, and the entire chemical reaction happens, and you will get a brown color thing called rust. As we all know that when rust expands, it induces stresses, and the cover concrete, which is more weaker than the core concrete, it will have a lot of cracks. And so that's why we see cracks and spall in the cover concrete rather than the core concrete in any of the typical structure from a slab or from any of the structure. With these basics, why the corrosion happens in a concrete particularly, I will go to the next slides. And because of this corrosion, what happens is you can see a 6 to 8 year old cooling tower with a lot of corrosion. You have a beam of a jetty, like soffit of a jetty. This is a typical pier of a railway overbridge which got corroded. And imagine what if this fails, then Gujarat's Western Railway main line will collapse. And you have a column which got having a lot of corrosion, still it is standing. And a collapse of bridge, a typical structural failure of bridge from the middle of the span because of failure of PT strands, which are highly neglected item in entire bridge structure nowadays. And one need to take care of this corrosion to avoid corrosion of PT strands, because it takes majority of the load, and when it corrodes and it break up, this thing can happen. We are supposed to protect this bridge, but because of the formalities and bureaucracy, when we are supposed to start before that, it fails. This is the condition of pile of one of the bridge, which is hardly 10 to 12 year old. And this is a new problem upcoming, like in a city, like mega city of Mumbai or Chennai or Kolkata, wherein this is a newly constructed building, wherein before people start staying it, you find this type of problem. Imagine you are spending crore rupee or 75 lakh rupees to buy a flat in this such type of multi-story building, and you see this structure, what will happen? This is just because of ingress of chloride or chloride admixed during construction. It may be due to curing water not taken care of properly, or it may be due to sand used which is having high chloride, or whatever the reason. But the chloride is there in first day, which is a cancer for the concrete, and it starts corroding the rebar, and then it leads to structural failure. We don't want this. We don't want these failures because of the corrosion. And what we do is we take care it by a jugaad. As far as Indian context is concerned, the parapets are painted properly, and there is a temporary support which is taking care of the flow of the water and taking care of angle of repose, 45 degree, and wooden logs. Fine, it will stay, but it will not stay for long. So to have a long and durable repair, a structure to stay with very, very minimal repair or simple protective coating or minor maintenance, it should stay there nicely for 25 years. That's the main issue. And if it doesn't, if we want to have the structure to have a minimal maintenance for 25 years, then corrosion has to be taken care. Corrosion of rebar has to be taken care in a particular RCC structure. Even if you have we have a standard practice of structural strengthening using CFRP wrap. And when we design CFRP, even ACI 440 says that unless until you don't take care of corrosion of RCC structure, which is going in inside the structure, you cannot do strengthening using CFRP system. And it fails. We had various examples, what we can see on the screen. And to go for any repair, I will have just one slide or two slides for the health study corrosion survey. When we say like I had done NDT, it should not be confined to only UPV and rebound hammer or maximum core strength. You should have a proper corrosion survey. You should find out what is the reason of damage or reason of distress, cracks, falling, or whatever failure is there. You have to go a holistic approach of NDT using what is the corrosion probability using half cell potential. You should know what is the existing cover, what is the existing strength, what is the chemical analysis, how the cracks are there, and corrosion rate of the concrete, what is the concrete corrosion rate of the steel, and what is the concrete resistivity. When you take all this NDT and then you interpolate and have an simultaneous view, and then you find out what is the reason, you can be having a very good solution for this. Like there was a study being carried out, and we found along with IIT Madras, and it was found that most of the structure, majority of structure fails between the repair part fails once the corrosion has initiated, and in propagation time when we repair it, it fails within 4 to 5 years, majority of the structure. And very few structure have more than 7 years of life. We don't want this. We don't want main structure repair or repair of repair and again re-repair. We should have a structure repaired at least considering the life of 25 years, 20 to 25 years based on the economics and value engineering and importance of the structure. So that has to be taken care. And how it can be happened. People are doing this thing. We had some structure being done. I will show you some case studies. Right rehabilitation comes in the picture, like serviceability, structural stability, and durability. We have to take care of durability. That is most important. And durability comes in the picture. Even IS code has limited steps for the durability or performance point of view, wherein people are, many people's academics are trying to have a durability and performance criteria for designing of the structure. So corrosion and initiation of corrosion or propagation of corrosion time has to be taken care. So if saying this as a base, like when we say corrosion protection system, apart from protective coating or using some corrosion inhibitor, like which is trying to delay the corrosion activity by some time, maybe from the months or to the 1 to couple of 3 years or 4 years, also which need regular maintenance. And again, competency of the quality of the coating and 100% sealing the surface area is always a question mark. So we had various other systems in the form of cathodic protection for RCC structure for durable rehabilitation. It can be an impressed current cathodic protection. It can be a galvanic corrosion protection system or electrochemical treatment. Like impressed current cathodic protection system is wonderful system. It's very good for all the steel structure. But when it comes to reinforced concrete structure, there is a huge complexity because we have steel varying from footing to slab and everywhere, and there is always a walls and other things. So continuity of the steel, amount of steel, zoning and designing is very complex. So it's not good for all the structure. It's wonderful for many of the structure, limited structure. But when it comes to galvanic corrosion protection system, it's like in ICCP, you have an external power supply. When in galvanic corrosion protection system, you don't have to give any external power. The anode which are embedded in the concrete itself give you current, and then it can protect the corrosion of reinforcement in the steel. In case of electrochemical treatment, we can change the chemistry of the concrete. Like if there is a chloride ingress in the structure, we can remove the chloride from the concrete. Or if the alkalinity has gone down, the pH of concrete has gone down to 9-10, we can realkalize the concrete. There are Norcure system available and we can do that thing. when it comes to corrosion protection system, there are level of corrosion protection. Like we say concrete, I want to do concrete, but which type of concrete I want to do. Similarly, corrosion prevention, corrosion control, and cathodic protection. As you go down, like you go the higher level of protection, you need a more current and more enhanced type of system, advanced system. So we will see some example of corrosion prevention, corrosion control, and corrosion protection. Corrosion prevention means you don't want a steel to start corroding. So you need very less current. And if there is already a corrosion going on, you want to control the speed of the corrosion, which comes under corrosion control. And cathodic protection is whole structure, foolproof system, wherein you can take a risk. Definitely it comes with a higher cost. And depending upon considering the structure importance, we can go for any of the system. But before deciding the system and what level of protection we want, we should understand how to design. I cannot, like in a small time of 25-30 minutes, I cannot explain you entire design thing, but I can share you the basic points one should consider before selecting the corrosion protection system. Like one should know what is the location of the structure. It is how far from, like it is Chennai, it is a Delhi, it's a different case. Chennai is located to the chloride contaminated things. If you go for a city called Ankleshwar in say Gujarat, wherein there is a lot of chemical industries, or if you go to New Delhi, there is a lot of carbonation effect than the chloride. So you should know what is the location, how far from the contamination, what is the type of a structure, and what is the extent in the structure as of now. So we can have a proper value engineering. Corrosion study report doesn't limit it to only, it doesn't include rebound hammer and UPV. We should have upsell potential, we should have chloride content, we should have corrosion resistivity, concrete resistivity and corrosion rate of the steel, and cover what is the level of contamination. As you all know that our IS says 0.6 kg per m³ of chloride is good, is a threshold or is a limit. The chloride should be there. It should not be more than 0.6 kg per m³ in a concrete. Otherwise, it is detrimental. But what if there is a 0.7 kg and what if there is a 2 kg per m³ in of contamination in the concrete? So you need a different type of design based on the level of contamination. And then steel density. Steel density, please don't misunderstood by the weight or diameter of the steel, cross section of the steel, which is a structural parameter. When it comes to durable parameter, you should know the surface area of the steel, because we want to protect the surface of the steel from corrosion. Property of the concrete also comes in the picture. If you have a very high grade of concrete or use various type of fines or replacement of cement, then the resistivity changes. Or if you have other type of concrete, then resistivity changes. You should consider property of concrete for the design criteria. Design life. This is design life of the anode. Like anode should function for 20 years, 25 years. So you can have a corrosion-free life of the structure for 25 years. That is what I'm emphasizing. If you don't have corrosion of rebar, I'm doing this repairs rehabilitation since 25 years, almost 26 years. And I found that 75% of the structures are having failures or distress mainly due to corrosion. And if you can delay the corrosion for a long time, you can have a less failures and good structures. So design life of anode to be considered, level of protection, which I explained earlier. Installation limitation, if access is not there or if you need to have other non-structural changes to be done to install the anodes, then it comes in the design criteria. Regarding the performance criteria, like once you design the system, how one should know as a designer that in which way my cathodic protection should perform. How I can say that yes, it is performing. When you are doing a corrosion prevention, then current density comes in the picture. EN 12696 says to apply a current of 0.4 to 2 milliampere per meter square of steel surface area, then you are preventing the corrosion from initiation. So current density in case of corrosion prevention, and in case of corrosion control and protection, current density as well as potential shift, that is depolarization. If you are able to depolarize for more than 100 millivolt in 24 hours of system, then you are protecting your structure. So these are the performance criteria. we should be able to monitor the system so that we can know that yes, whatever I had spent for preventing the corrosion of rebar, it is performing. And residual life, like even after the consumption of zinc in the anode or a metal in the anode, you had, by doing sacrificial anode system or cathodic protection, you had make the pH good. You had make the environment around the steel good for the corrosion protection. So you can have a residual life after the consumption of anode also. It will have a long time, few years more for reinitiation of corrosion. And value engineering, like how much money to be likely to be spent. Again, if I go to the same corrosion cell, what I had showed you earlier, and what we are doing for the patch repair, we have a proper saw cut, we chip out, we clean the rebar, we go beyond the rebar, apply various protective coating on the rebar, and use a chloride-free patch. By doing this, what we had done is we had introduced new condition wherein the new patch and the non-contaminated area will be having a similar half cell probability of corrosion, but the concrete which was not cracked and having a contamination adjoining, which we didn't remove because concrete was good, it will have a more negative half cell potential. Because of this difference of potential, what we say is delta. If you carry out half cell potential of any of the structure, and if there is a quite variation in the half cell potential of adjoining readings, like what we have here 200 and minus 350 for sake of understanding, if there is around minus 100 millivolt difference, then which is a very high difference, and there is a very fast corrosion rate, very fast movement of electrons in presence of water and oxygen, so you will have a high rate of corrosion of rebar. So if sometimes you might consider that I have a half cell potential of minus 450 or minus 350 all of the structure, and the delta is not high. Like you have all around, you have minus 350, minus 360, minus 370. So because of less difference of half cell, you have a very low rate of corrosion and you don't see cracks. But you will see cracks even though half cell potentials are minus 300 also, you will see the cracks because the delta was high. So difference of half cell potential comes in the picture. And in this case, by doing the patch repair, what we had done is we had induced the corrosion in the adjoining good concrete, or like good concrete which is having steel with contamination will get corroded. And this is called halo effect or incipient anode formation. And you can see there are two patches for one patch repair, and the road around the right side is repaired n number of times because of halo effect. We don't want this. So this patch stays for only a few years and you had another repair. And if you want to have a long-term repair, what we need to do is that we need to incorporate some system. We can use galvanic corrosion protection system, which is an innovative and advanced concept, and it is good, very good for atmospherically exposed concrete. In case of submerged concrete, we don't have much of a free oxygen available, submerged in the water. So there the corrosion rate, particularly in the deeper the sea, is less. So we are the zinc will corrode because of very high negative potential, and it will not allow reinforcement from corrosion, and you can have a durable and good patch repair. Like this is how a normal patch repair we do proper cleaning, saw cut and soaking and apply the mortar. The additional thing is you have to just to tie an anode like this. After tying, you just check the connectivity, whether it is properly connected to the steel. At the connection, the steel should be cleaned properly and there should not be any coating over the steel. So this has to be ensured. Otherwise, this anode will not function. Whether I had seen various people where the anodes were loosely connected or anode were lying outside. You can see the anode is inside the concrete cover, like there is a proper cover over the anode so that ionic movement can happen from the cover part, and the steel is properly connected so the anode will function. Like we had one beam installed in 1999, Lester, and we are monitoring since about 22 years. What I'm telling is based on the factual data, what has been considered, what has been installed and monitored and analyzed. So we found that at the 20 years data shows that this type of anode can give a current density of in the range of around 1.2 to 1 milliampere per meter square, which is as per the EN 12696, and it is protecting the structure. These anodes were designed earlier for 15 years, it's protecting up 20 years. So this shows that we are passivating the steel better over years when we use sacrificial anode system. There can be a longer similar discrete anode which can give you a higher current. It can be distributed anodes, a longer strip anode which you can install when there is a high density, high amount of steel, or there is a high contamination. Then you can have a more current requirement, and so we need a longer anodes. And if you see that the discrete point anodes have a pink line which is having a lesser current, which is good for prevention. When it comes to cathodic protection, if you use a longer rod anodes, it gives you very high current as per the requirement, and it functions wonderfully. I will show you a few case studies now with basics like the majority of corrosion failures are due to corrosion. Why corrosion happens in a concrete structure? You should take a proper NDT, and there are various cathodic protection system available, ICCP, sacrificial, electrochemical treatment. And normally we had found with the experience of 20 years that galvanic based sacrificial anode system are very good in functioning and protecting the reinforcement corrosion. These type of anodes were available in India since around almost 2 decades or 15 years. And earlier we were not having much of an technical experience and backup because it was new technology. But I will thank Dr. Rajendran that he has introduced this system almost 12 years back. And he was supposed to repair one jetty which is 20-year-old at Chennai. And they found out that the chloride concentration was very high and there was significant mass loss of steel, and reinforcement were supposed to replace. So they just added a point anodes here. The design was done now with experience, we had further rationalized the design, but the design done was 1 unit per meter square, and even monitoring box was installed. And this is how the work was done. Concrete jacketing was done in all new reinforcement. Anodes has been installed. What we did is after 12 years, even along with the IIT team, we had a visit there, and we found that there was no severe corrosion damage in the same structure where it was jacketed. Electrical measurements were taken, and it was found that the corrosion, the anodes are still protecting after 12 years, and within very, very high spacing, which we normally don't recommend now. But earlier we were having some limitation, but still it is functioning. Imagine we had checked there for 4 years as per the contract, and we found that there was depolarization potential of more than 100 milliwatt. So it shows that 4 years anode were performing, and then anyhow the monitoring was not possible. But after 12 years, we see physically there was no significant damage, and the current was measured. Still, the various 8 locations we are having a good current after 12 years. So the anodes are functioning. We can, if somebody wants, somebody can have a boat and visit the same structure even now also. Imagine in an 8 year of service life, there was a significant damage. And when you repair it, after 12, using sacrificial anode system, after 12 years, you have very minimal cracks, not major corrosion problem like what it was there in 8 years. So this type of repair are required. A professional approach has to be done. I must thank Dr. Rajendran and IIT, Dr. Radhakrishna Pillai for helping me with these surveys and these slides and pictures. And wonderfully, it is working nicely. This is what we want. We want an enhanced repair life. And when it comes to cost, the entire cost analysis has been done, and it was found that CP anode cost was hardly 3% in the entire structure. Imagine by incorporating 3% or save even 5% of the cost, and if you are saving your 95% cost reoccur after 5 years or 7 years, and it occurs after 25 years, you can imagine how good value engineering has been done. Another structure is in Tuticorin, wherein this is a salt processing factory, and in case of salt processing factory, you have a lot of chlorides and various problems. And it was repaired using CP system. These are the before and after photographs. Definitely, there were very high chloride concentration, continuous exposure to chlorides. And conventional methods, we don't. There is already a chloride inside and high corrosion activity. So it will fail because of patch acceleration or halo effect, and you can see the various cracks. Like here again, the anodes has been installed, and the anodes has been installed, and then zinc-rich epoxy coating has been applied. But obviously, spacing is very high. This was done about 10-12 years ago. I told you that we are having now we are having more rational design, and then the normal jacketing has been done. The only thing is adding this anode, nothing else. And there was monitoring box, and we had measured the regularly monitoring the corrosion, the current from the anodes, and it is performing. And again, when we do the cost analysis, entire cost, the CP percentage cost was very low compared to the other part. So we should have we had found and even published the paper that the cost of CP might seems to be high initially as the unit cost, but when it comes to entire repair system cost, it's a fraction. So this I had shown you where there is a patch already spoiled and there are cracks. But while doing your NDT, you come across that structure is good, cracks are not there, but there is a contamination ingress. In that case, you need a high initial current and you want to control the corrosion. So you need different type of anodes which can be drilled and inserted inside the anode with the special connectors. Like this, a type of pre-stressed box girder where there are patch and there is a good concrete. So which are away from the patch, you need to protect. You can have a drill and fix anodes. This is how they are. Like why I'm showing this presentation is of Dubai, which I had done, because nowadays you had a lot of multi-story buildings in Chennai and basements are there, multi-story basement, which are having a lot of issues with the corrosion. Imagine this water which is coming out from the subsoil water is having a lot of chloride. What will happen to your basement structure? So when I visited one of the basement in Dubai, we found that the corrosion stains were there and water was leaking. There was no cracks, there were no spoils, but we see the corrosion brown rust. So consultant asked us to do the solution. I says, even if you arrest the water, you won't have a bone dry condition. If it is bone dry condition, it's wonderful. But as already leaking is there and you are seeing the rust mark, so corrosion has initiated and passivating layer has gone off during the construction time only. So we carry out thoroughly NDT with all type of taste, and we even taste the quality of water, which was having very high chloride content. So it was decided that CP has to be done. And we use corrosion control system, wherein the anode is having very high surface area. What we did is we marked entire steel on the wall and the affected area, and so that we don't cut a single steel. So structurally, the raft and the wall is safe. Then we find out the area where the half cell potential are more negative and delta is high. And then these are the green lines. And then we drill the hole between the rebars. I'm sorry. So if you see the right hand side picture where the red lines are the steel and the hole is drilled, and the small hole in the green is the connection with the steel. We use special steel connector so that the steel is connected to the anode, and the anode are also connected to the steel with a special button connector, so that the joint of the wire is also not get oxidized over a period of time, and the connection is proper for 25 years. This is what we want. So we take care of every small thing, a proper connector using steel for the steel connection, then a button, gel type button, and the anodes without cutting any steel, and then it is sealed with the mortar. We check the connectivity at all the levels, and the connectivity should be less than the voltage should be less than 1 millivolt if they are properly connected. So you need to check the steel to steel connection in the concrete. You need to check the anode to steel connection in the concrete, and then seal the surface with the low resistivity mortar, and you don't see anything on the surface. Simply paint it. You can install the monitoring box, you can take the readings, and you can see that your system is performing. No external current, only a small piece which is embedded inside the concrete, and you can save your basement from the corrosion for 25 years. So this is a good thing which fails, which might comes as a failure in near future in Chennai or other part of the world where the multi-story basements are being constructed, and leakage is the problem. Another case study I'm showing you is for the jetty repair. This is for IFCO Kandla, wherein the piles were corroding. The sacrificial liner has also corroded, and they had induced cracks and spalling in the piles concrete itself. And we had considered the height of pile jackets. We had used special jackets imported from Canada. We had considered the height of jacket as 5.5 meter because tidal variation is up to 5.5 meter there. And we had installed the jacket from the bottom of the pile muff up to the minus 5.5 meter, and bulk anode was also installed at minus 6 meter to take care of very high current demand over a period of time. The system was designed for 25 years, and steel surface area was calculated. This is the photograph. You can see the first left-hand side photograph, which has a tidal variation of 5.5 meter left and right photograph. Then the scaffolding was erected and the steel liner was cut. Right-hand side photo, you can see the last photo, the removed steel liner, and the concrete is having a lot of corrosion stains and some cracks, which has been cleared with the water blasting later on. And the anodes has been installed on the surface of the column. The first left-hand side photo shows the strip anode with an special fabric over the anode, which will have a keep the anode like we want the anode to corrode, zinc to corrode. So by wicking action, this cloth will keep the anode corroding. And then there is a bulk anode, the center and the right-hand side photo, and special modular jackets has been installed, which will stay in place. And then the concrete has been filled between these infills of the old column and the new jackets. So it's a simple jacketing, but with the addition of special anodes with the wicking action, a bulk anode at the bottom of which will be there in the water, and a PVC modular jackets. And then you simply close everything. We are monitoring the system as of now. And if you see that instead of 624 and 24 hours is 505, so the row number 8 and 9 or 7 and 9, the average half cell potential, it shows that there is more than 100 millivolt polarization, and current was also, density was everywhere more than 5 milliampere per square meter. So we are protecting the, it's already 2 years back now, and it's working wonderfully. And we hope that definitely it's going to work there for 25 years. Another is the heritage structure, wherein Dr. Radhakrishna Pillai was consultant. We had also there and been installed by another applicator, distributor of Vector from Ahmedabad, being in North India. Imagine such type of heritage structure where there is an issue, you cannot change the structure. You have to be placed, you have to make it as required as it is as built condition. And if there are problem like this, which is because of the carbonation effect, you need to have a proper connection of rebar and develop a system which will definitely protect it for 50 years. In heritage structure, we talk of centuries. At least if we can install an anodes which will work there for 50 years, and in contract itself, the 20 years guarantee has to be given by the contractor. So to develop that system, we carried out one pilot project wherein cantilever reinforced concrete sunsets with high corrosion of rebar and delamination of concrete were there. And earlier repair has been done, but they were failed prematurely. And lime concrete was there. It was not cement concrete. So it was difficult for us to design the system. But we tried with the pilot project with various options, and we find it more successfully. We develop a system which has a longer life to protect any reinstatement which has already been done from premature failure and retain the shape and size of the structure to avoid the reconstruction of entire elements. We use different type of anodes, and we did monitor for 2 years. This was the design, how the anodes has been installed. Like if I show you various photographs, first of all, we had located the rebar using GPR. Then we checked the half cell potential regularly in the grid pattern. Then we checked the connectivity of the rebar. All rebar were not connected. So we introduced special rebar connector at the top, and then we connect all the rebar with a wire, and they were embedded, and we check connectivity of all the rebar, like every 5 centimeters, 7 centimeters. We introduce the rebar connector and we check the connectivity. Then we make a small chase for installing the anode, and the anodes have been installed. Again, the connectivity of the anode has been checked, that whether anodes are connected properly. And then we also install one embedded reference electrode, so that we don't need to go there using surface electrode for measuring half cell potential. And these are some photographs of checking the connectivities. And then finally, the anode has been covered with low resistivity mortar, and overlay has been laid because there was very less cover. So we need at least 20 millimeter cover. So 120 overlay was been laid over that. We had a person from North America who is CP4 to assist us in installing this type of anodes. And the key benefit is that there are 2-stage anodes. These are the special fusion anode, which will act as an initial very high surge of current, and then it will automatically convert into sacrificial mode. So there was no external current, and we are able to passivate the steel in a very short time period. So so that's the most important thing, and enhance life of the structure, because the initiation of corrosion has been delayed. And this is all our alkali activated anodes, so there are no harmful effects to the concrete. Further, we had installed the monitoring box, and we are taking regular current measurement and half cell measurement. And we found that the initially stage 1 up to 100 days, it was having very, very high surge of current, and we got very good potentials, negative potentials, and then automatically it converted into sacrificial mode, wherein the low current is required, but everything was as per the ACI what you can say, passivate the reinforcement, and the system is working wonderfully. And the now full stage project is going on for such heritage structure. I will just have a few slides for a typical failure which is not having a corrosion effect. It's a design problem. When the building under construction, there was a typical punching shear failure. You can see a shape of failure. This is because of that a person forget to mention the required steel in the drawing, and then this leads to such type of failure. All data analysis has been carried out, and the constraint was that what I mentioned, designing for strengthening, was that 3 floors were constructed above the distress slab. So we need to consider that also confidentially, but obviously multi-story commercial building, nobody will purchase if it is a public thing that there was a design issue. And it has to be considered in 45 days only the work has to be done. I will just quickly go. The additional drop has been constructed around the column by making a shear connectors as per the design. Even shear connectors has been designed, and roughening of concrete has been done for 20 millimeter amplitude, so that the shear transfer has been taken as 50% by the roughness, and the remaining 50% has been taken care of by number of, like there were 8.9 number of shear connectors were required. So we use 9 shear connector per meter square. And then after roughening, installing shear connectors, and some area where it was highly damaged was broken out. And then we do shuttering, and the concrete was poured from the top by making a drill, micro concrete. And the drop was created, new drops. Also, we find out that there was positive and negative moment deficiency. So we cut the steel, and near surface mounted carbon fiber strips were installed from the top, and cost was the constraint. So what we did is we cut from the bottom, and we installed the rebar in the bottom soffit of the slab, like 12 mm steel. We use what we do, rebar grouting for the embedding for the new steel connection, horizontal hole, like we drill 20 centimeter, 30 centimeter hole and insert the steel. This way, we insert the steel along the length for 3 meter and 4 meter, and 10,000 meter of steel was insert on the soffit, and the building is standing wonderfully. It's perfectly standing. This was done by me under my design and installation back in 2009. And the system is working wonderfully since last almost 12-13 years. If I say the CPACE usage in India, we are using since 2002 and it is growing exponentially, and it has been used, people are adopting the system, so there is no harm. And there are various buildings like chemical plant which has been installed and done. Institution building also you can use such type of anodes. You can use along with the strengthening also, you can use the anodes so that to have a longer life. This is again a bromine plant. This is a chlorine yard wherein the damage was there, and micro jacketing has been done along with fiber glass fiber wrapping and anode so that we can have an enhanced life of the structure. One of the building in chemistry building and in IIT Madras wherein anodes has been installed. This is the anode. But how to select the anode? Like your anode has to be properly having an activating mortar which should keep zinc corroding. It should have an alkali material. It should not have halides or salts, and it should keep zinc corroding for 25 years so that the pH of for long-term connection should be there with the anode, so that when zinc is corroding, you have a connection of rebar and the zinc for 25 years. It should not be welded. It should be casted inside the zinc anode. If you had a welding or screwing of the wires at the zinc, when zinc is consumed, this connection will go off and the anode will not be able to use. So this is a wonderful technique, but poor practice or poor material will give you poor experience and the whole technology will die. So before selecting the anode, you should know what type of anode I am installing, whether it will function there for years, not for the months. We have in tender or contract that anode of 1 year is the defect liability period. So after any anode will perform for 1 year or 6 months. You will not come to know for the new cracks in 1 year. You will come to know after 3-4 years, 5 years. So your anode should be such that it should perform for 25 years. For that, one should have a short-term test which can say that this anode is good. IIT has developed such gap test similar to NACE TM0294, and they had developed the test by applying various DC potential, and like for very high potential difference and low potential difference, they had taken 2 anodes from the market, and it was found that one anode was failing like prematurely in 60 days only. By looking to the anodes, zinc mass is same, anode looks same, but it fails in 60 days. Another good anode is performing and still for 100 days and is still performing. So you should select a good anode. You should get it tested, and then only you should use that type of anode so that technology has been maintained. So like what we say in Hindi is jung is war to a jung called corrosion. So jung se jung, it's a fight with the corrosion. Increase awareness for protection of corrosion in RCC. What I'm trying to do, I always agree for any lecture anytime so that we can increase the awareness for corrosion protection in RCC. There should be a predictive approach, not the reactive approach. What we do now is that we go and do the repair after we see the spalling and cracks. That is third level of corrosion. Whenever we see initial crack or raised turn, rust stain or something, we should immediately do the NDT. Increase know-how of technology available. This technology is available. Then there should be a specification at the design stage. We are trying that we can incorporate this is in CODAL also, BIS also. I will just conclude that India is in dire need of effective corrosion protection system. Corrosion prevention strategy need to be implemented in the new structure also. It can be a targeted protection, and the CP technology do not add significantly to the cost of repair. It can be considered as a complementary system. It is not costing as if somebody thinks that it is very, very costly. Repair using CP is economical when considering the life cycle cost, and the anodes available in the market must be assessed before installation. Use of poor quality anode can lead to reduced repair life and defaming the promising technology. This is very important. Any questions?
Good afternoon, sir. Sir, this is Dr. Guru Prasad here, talking from Bangalore.
Yes, sir.
Very good presentation from your side. First, congratulate you. Sir, I have 2 questions. One is, I just wanted to know regarding the corrosion, what you talked about. Now we have buildings, especially residential buildings, what I see in and around Bangalore or when I have traveled to different cities in India, after the construction, the rebars in the columns are left out. That is, they are left exposed. And
Yes.
for quite many number of years, it is left exposed, and I see the corrosion formation, the rust formation there. Now, in
Yes.
such cases, what can be done? So, because nearly around 5 to 6 years, the reinforcement is exposed, especially the column reinforcement, I see. So, in that case, if they are going to go for any further construction above it, you say by continuing the same columns, what are the treatments that can be given to such reinforcements? So that is one thought which was prevailing in my mind, because there are various anti-corrosive treatments like anti-corrosive paints also which are applied onto the reinforcement. But what I'm worried is when the reinforcement is exposed to the atmosphere and to the rains, seasonal rains, and eventually the corrosion would have propagated into the particular column. Am I right, sir?
You're perfectly right. Shall I answer first question, or you will have second question and I answer both the question together?
Yeah, my second question was, this was my first question. What can be done to restore such columns? Second, yes, sir, you talked about the near surface mounted reinforcement when, which you talked about with 12 mm rebars. Sir, I just wanted to know, you have made a groove and inserted the 12 mm reinforcement.
Yes.
And what is the particular type of epoxy or the filler material which you have given, and for anchorage of those steel reinforcements at the ends? I just wanted to know, please.
Okay, I will answer you both the questions. First of all, the first question, definitely it's an right observation by you, and we find that this is a big issue with various people, various places, not only in Bangalore, even in Gujarat also. I go anywhere, I travel pan India. Earlier there is one basic option is you don't keep the steel exposed. You can have a dummy low RCC, or you can have a properly covered reinforcement, or you cut the reinforcement and do rebar grouting whenever required. Okay, that is one thing.
Okay,
I would love that if you don't keep the reinforcement exposed to the to this thing. Now the second thing is, even it is exposed and you are having an extended construction over it, what will happen? That I come across such inquiry nowadays a lot because of this COVID 2 years of losses. People were not able to do the construction, and after 2-3 years now they are starting the construction. And if it is near the marine area, already the chloride has ingressed in the less protected concrete, which is already done through the rain, and it is passing through the rainwater, the atmospheric chlorides, whatever is there, is passing through the rebar and going inside and reducing the passivating layer of the steel, which is already embedded. Now, when you clean the exposed rebar and you apply any coating and you apply a fresh concrete, what you are doing is the new concrete is good pH, good protected steel. But the old concrete, old reinforcement and in old concrete is having less pH. So you will have a very, very aggravated corrosion rate, and you will have a start failure at that joint. Because of time constraint, I couldn't show that slide, which is old construction and new construction joint, wherein corrosion start immediately. Earlier, you won't find cracks, but you will find cracks immediately. In that case, if it is a medium-sized column of 600 by 600 mm or so, you can simply tie one anode at that interface and do whatever you want to do. That's all. So this anode will protect the corrosion. It will corrode itself. It will not allow corrosion of rebar which is in the concrete. That will be a great help to everybody. It will not cost much.
Okay, sir.
And regarding your second question, we use a special adhesive. It was that time, which is normally used structural adhesive. What we use for the bridge segment bonding, like if you have precast bridge segment which you use for bonding, that type of PC40 or phosphor or something like that, or we use for the laminates, that type of bonding has been, we are using that adhesive. And regarding your anchorage length, the designer along with the professor, that is Ashraf Bidda in Dubai, we had calculated the anchorage length, and we had kept that much length extra. Okay. And at the negative moment, we had done an U bar hooking from the top, like anchoring using U bar at the end. So we had 2 additional rebar in the form of U, and not allowed the steel to pop off in the negative area.
Okay.
That's what we had done.
Sir, I just wanted to know this Nito bond which we get for bonding the reinforcement into the grooves of existing concrete.
Yeah.
Then we use from first rock.
Yeah.
We make use of that.
No. You can't. It comes in a liquid stage. You can't use a liquid.
This will be more of a semi-solid, pasty kind of a tacky,
this
tacky
is a dough consistency.
Yeah, with a tacky consistency, right?
Yes.
Okay. Sir, what is the name of this? As you suggested, sir, the epoxy. I'm sorry.
You can use Nitorap 40.
Nito?
And a custom-made phosphorus, you can use Nitorap 4040.
Oh, Nitorap 40. Okay. Thank you, sir. Thank you very much.
Yeah.
Thank you.
I will be publishing a paper and again announcing, because I'm doing such one project in Baroda, which will be finishing in a couple of months, and then I will have a more detail.
Okay.
We are increasing the moment taking capacity of column using rebar vertical grouting. Like we are putting the rebar in the column for the full length of the column and the beam.
Okay.
I'll be doing that thing.
Okay, thank you, sir. Because I too work in the field of non-destructive testing and repair and rehabilitation of structures, adopting CFRP, that is composites as well as into RC.
You can have, you need to go in more economical way. You need to go in like inserting the steel rebar or FRCM now. All the CFRP and glass fiber has to be go now.
True. Sure. Thank you. Thank you very much. Have a good day. Thank you.
Same here.
Thank you very much, sir. Thank you for bringing a newer addition in the field of cathodic protection, especially on hybrid anodes. It can supply a high amount of charge. Yes. Yes, sir. Proceed, sir.
Yes, sir. Actually, very good presentation, sir. Actually, I want to know, because so many corrosion is available, is there no material like ever silver to use as an alternative or steel to have corrosion-free reinforcement?
Sir, can you repeat, please? Alternate steel?
Actually, our steel bars are getting corroded, and we are going for so much of treatments and other things.
Yeah.
Ever silver. Actually, I read some long back. In atomic power stations, they'll use ever silver steel rods.
Yes.
So that it won't get corroded.
Yeah.
Is it not possible to use in wherever it is prone for corrosion?
Definitely, yes. You can use fusion bonded steel. You can use stainless steel. You can use GI coated steel. But all has its own advantages and disadvantages. If you use fusion bonded epoxy, then you should have a banded steel and then done fusion epoxy, fusion bonding, right? Because if you have a straight steel and if you do bending and then the bending area got damaged or cracked, or if it is not handled properly at the site, there will be a lot of holidays, and then the whole good steel will be creating very high corrosion. If you can use the galvanized steel, same thing, but the cost comes in the picture. And you can use the stainless steel rebar. Yes, definitely you can use. One of the structure in Delhi has used stainless steel rebar, but cost comes in the picture. So we have to work for value engineering also. We cannot spend like 3 times or 5 times the cost of rebar for to avoid corrosion. If we can have a less economical system which can avoid or delay the corrosion for 50 years, it's good, na?
No. Actually, the ever silver bars will be more 10 times costly than normal bars.
So stainless steel cost is what, like how much you will cost? Normal steel is say 50 rupees. It will cost you 300 rupees or something like that. Maybe 6 times cost. If I'm sorry, 10 times, maybe 6 times the cost. You see the cost of SS and my steel. Compare the cost. That's all. And because it is not easily available, so manufacturing cost is also high.
Oh. Thank you, sir.
Thank you.
Thank you, sir. Is there any other questions from the participants?
This is my mail ID. If you have any other questions, you can mail me on dhruvesh@vectorcorrosion.com.
Sir, thank you so much. Thank you for bringing a new insight on corrosion technology, especially on suppressing the escape of ferrous ions from the steel bars and prevent the formation of corrosion. Thank you, sir.
Thank you. Thank you for allowing me to give this presentation.
Thank you, sir.
If your actions inspire others to dream more, learn more, do more, and become more, you are a leader. I take the honor to welcome Dr. Kattankulathur to introduce our next speaker, Professor Er Santakumar, former professor and dean, Anna University.
Thank you, Pavitra. It gives a great privilege in welcoming our fourth speaker, Professor Dr. Er Santakumar, who doesn't need any introduction. And he is a former dean and chairman of Faculty of Engineering, Anna University, and a former professor emeritus in IIT Madras. Professor Dr. Er Santakumar obtained his MSc Engineering from the Madras University and his PhD from University of Canterbury, New Zealand, as a Commonwealth Scholar. He was advisor, Shelter Reconstruction and Rehabilitation, United Nations Team for Recovery Support, UNDP India. He is a consultant and also professor at Center for Disaster Mitigation and Management, Department of Civil Engineering, College of Engineering, Gindi, Chennai. He has set up a Center for Disaster Mitigation Management with assistance from UNDRO and Building Technology Center with assistance from ATCO at Anna University. He introduced MS by Research and ME in Construction Engineering Management in the Department of Civil Engineering, Anna University, for the first time. He contributed a number of research papers to national and international journals and delivered many invited lectures in New Zealand, Australia, USA, Singapore. He has coordinated the International Conference on Disaster Mitigation Management during 1997 and a number of workshops in the field of concrete construction. Besides teaching, he guides many PhD students and provides consultancy to many organizations in concrete construction engineering problems. He has designed a number of infrastructure projects such as bridges, shelters, towers, and plans for major public sector corporations, railways, and also for Government of Tamil Nadu. He has received ACC Nagadi Award for the best book published on transmission towers, McGraw Hill, Singapore edition, through Association of Concerned Civil Engineers, India. He has also published a very popular book on concrete technology, Oxford University Press, which again received the ACC award. Recently, he was acknowledged as an outstanding academic person and was awarded the prestigious Vishwakarma Award of Construction Industry Development Council. Thank you, sir. With short introduction, I request you to start a presentation, sir. Thank you, sir.
Thank you very much for the nice words of introduction.
Thank you, sir.
I once again thank all for giving me an opportunity to present a few of the case studies in which I was involved during my last service of 25 to 30 years, both at College of Engineering, Gindi, as well as at IIT Madras. I would like to share my screen now. I hope you are now able to see my screen.
Yes, sir. Yes, sir.
I have titled the topic as Case Studies of Failure, Repair and Rehabilitation of Structures. Mostly, the failures have been analyzed, the reasons for the failures have been found, and it gives us a method of knowing how to avoid such failures in future. What are the problems that cause failure? What are the causes of failure in general in buildings in and around Chennai is what we have tried to list here. One of the major problems is non-engineered buildings, then faulty original design, lack of lateral load resisting elements, in multi-story buildings, especially lack of shear walls, changes in codal provisions over the years of time, inadequate detailing of reinforcement. Many times, extensions, alterations, and encroachments are made without proper design, increase in load during usage. It is designed for a particular load class, but actual usage, the load becomes more. Poor and deficient construction, lack of regular maintenance, degradation of building materials, especially corrosion. These seem to be the major problems which cause failure in buildings. The first failure I am going to examine with you is Moilivakam building. It is a 10-story building. Two similar units were built. One collapsed, the other was standing. It was a big debate whether that building which was standing should be rehabilitated or should be pulled down. Even though there was a possibility of rehabilitation, it was finally decided that the building is pulled down and a new building is constructed there. We will see. I will narrate the incidents of the failure of this building. On 28th June 2014, a 11-story building collapsed in Moilivakam near Poru at around 4:30 p.m. after the onset of strong winds coupled with heavy thunder. This is the building that has collapsed. The collapsed building you can see in the foreground. The other unit, very similar to the one which had collapsed, is still standing. You can see the standing building, and immediate number of people got trapped in the building, and government initiated a committee. I happen to be the person who headed that committee, and what I am going to show to you is some of the findings that we were able to get from this collapse of this building. The disaster area was observed first from a nearby building. The government initiated rescue efforts, and the rescue efforts were in full swing. Two buildings were spaced at 23 feet from each other. One of them had torn into two and fallen down. Even though the two buildings were only 23 feet away from each other, there was no serious concern or requirement or study on how the wind pattern around the two buildings were changing because of the adjacent building. This was one of the major deficiencies, because we found that the two buildings were built within the influence area of the wind flume. A few eyewitnesses recounted the crash of the building. There were a few theories explaining why the building fell, but ultimately we did a very detailed analysis. The reasons attributed are design, execution, improper materials, and finally the loading that would have caused the column to buckle. In order to further understand the reason behind the collapse, a team of 5 members, 3 from CREDAI and 2 experts from Anna University, visited the site. A PWD soil expert deduced that the soil condition on which the building stood was good. Observations were made in 2 structures, one on the existing structure which has not fallen down, the other on the failed tower. It was felt that more or less the type of materials used, the type of design were similar in the 2 buildings, and therefore the standing building was used as a benchmark building to benchmark why this building, which was by the side of the standing building, failed. The size of the building was around 75 feet by 125 feet plan area. The size of the columns and beams were around 300 millimeter by 450 millimeter. The one building that was standing had 2 substructures connected in the middle via lift and a staircase. There were two substructures connected by the lift. It was interesting to note that in this building, the beams that connected the two substructures were linked only at alternate floors as shown in the original picture. You can see this is one tower, this is another tower. The two towers were connected. It was connected at alternate floor level, not at each floor level. Not only that, there was a void which permitted a huge amount of wind to go into the building and create internal pressure inside the building. We observed that the building had fallen into two parts divided at the center. One half of the building had fallen as a pack of parts, wherein all the 11 floors had come down one over the other, while the other half of the building had fallen in the opposite side. The building also had columns that were not erected in line with the center point of the columns that came from the basement. Instead, the columns were skewed to one side. The span of the beams was around 30 to 35 feet, and the depth of the girder used was only 450 mm. To this beam, another cantilever beam was also connected at the midpoint, which would further create stresses at the existing structure. You can see this is the column coming from the basement. The column coming from the basement central line is different from the column that goes from the ground floor onwards. So the difference in central line distance was at least 15 centimeters, that is around 6 inches. That creates a moment on the foundation from the 10th floor load that comes on the column. The basement floor was intact. The lift wells were made up of brickwork instead of shear wall. There was a lift well. This lift well was made with 4 columns at the 4 corners with infilled walls, concrete wall, and there was no mechanism in place to limit the shear force, especially in the stilt floor. Now, you can see the span of the beam is from here to here. Originally, there seemed to have had a column here in the stilt floor, but for some reason or other, this column has been omitted or removed in the subsequent construction stage, increasing the span of the ground floor beam to double the span, which is nearly 12 meters. And this seemed to be one of the causes for initiating the failure. Another cause was the opening and tying the 2 towers only at alternate floors. This shows that huge span. This is the stilt area where the failure had occurred. We measured the deflections of the existing tower and showed that the deflections were far in excess, even for serviceability limit, even without any live load in the building. At the time when we inspected, there was no live load in the building. The building was cordoned off. Now, this is that lift well. You can see the lift well had only columns at the edges and also had only brickwork as an infill wall. The outer beams, especially in the toilets, were punctured with 100 mm holes at 4 places within a span of 5 feet all around the building, exposing the stirrups and beam rods. In order to bring out the silage pipe outside, which was roughly around 6 inches to 8 inches, all the beams had been punctured. And because of this puncture, shear reinforcement had been cut and removed. And in some places, main reinforcement had also been cut and removed. This is the beam, you can see how the puncture has been made, and you can see the shear reinforcement is also cut. Here you can see the main reinforcement is also cut. The quality of concrete appeared to be micro concrete. That is, we did not see any 20 mm aggregate. The aggregates were all 6 mm down, initiating a feeling that the concrete is not a real concrete, but is a micro concrete. We examined very closely the failure points. This is one of the failure points. The failure point is beam getting into the column. When we looked at the beam getting into the column, this is the plastic inch zone. And exactly at the plastic inch zone, failure had occurred. And the plastic inch zone, steel should have yielded. Steel did not yield because there was no sufficient development length for the steel. The steel had been pulled out. Because of insufficiency of development length, all the steel had pulled up. Not only that, the required confining steel at the plastic hinge has not been provided. You can see that the stirrups that has been provided is in large distances, not introducing confinement to concrete. The size and spacing of stirrups is what has happened. The column reinforcement lapping were not staggered. We expect the column reinforcement to be having detailing in such a manner that the reinforcement is staggered. That is, the lapping has to be done in the middle portion of the column, and the lapping should be done not in all the four corners, 2 corners in one story and 2 corners in the other story. Such staggering of lapping has not been done. And not only that, the lapping has been provided in the plastic inch zone. Because the lapping had been provided in the plastic inch zone, the bars pulled out and the bars did not yield. This is the column which has fallen down. You can see all the bars have been lapped at the same cross section and not staggered. The beam depth was not continuous. We observed that the inner beams were only around 300 mm. You can see the beam depth here and the beam depth here do not match. Here the beam is deeper, here the beam is shallower, and the level of the beam is also not uniform. The design of the floor plan at the staircase and lift was done in such a way that walls constructed from east to west formed a barrier for wind and light striking in the north to south direction. This leads to suspicion that the wind striking at a high force would have struck odd against the east-west walls, thus causing one side of the building to fall. You can see openings invited wind to go in. Now, how did the collapse occur? The collapse is a typical what we call as a pack of cord collapse. You can see the collapsed building. You can see actually all hinges have formed in the columns. Column bars have been pulled out and beams bars have been pulled out. No plastification has occurred in the beam column junction. Nowhere there was yielding of steel. This is what was surprising in such a big building. All because there was not adequate development length and anchorage length given at the ends of individual members. This we call as non-ductile beam column joints. You can see the non-ductile beam column joints just pulling out and This is the non-ductile beam column joint. Here also non-ductile beam column just pulled out. Now, in many places, bars had been kinked and taken inside the column, and the kinked bar did not have any capacity because before it has to take its load, it has to straighten out. It could not have resisted any load, and hence the plastic hinge had formed here. In fact, this is the right type of reinforcement detail that they should have adopted, but they did not adopt this type of reinforcement detail. This type of reinforcement detail with no lapping was adopted, and hence it was easy for the force to pull out the beam. See, in many buildings, this is the building which was being constructed elsewhere. You can see how the column reinforcement and the beam reinforcement is not aligned. The column reinforcement, the column central line and beam central line are not aligned. The beam is pushed to one side. This is a very serious issue because this creates a bending moment on the column, making the column to fail. This is another place, multi-story building where we had witnessed vibration was done not in a scientific manner, expecting good amount of consolidation of concrete. Instead, over vibration was done, and because of the over vibration, all larger particles had settled down at the bottom, and only 6 mm down particles have settled down at the top, indicating that several beams are suffering from the problem of segregation, with the result, when we checked the core strength in the top reaches of the beam was where maximum compression comes in the beam was only around 10 to 15 MPa. And this is one of the reasons why plastic hinges could easily form with the compression failing and tension bar being pulling out. Another failure, this is the next case study. This case study is Chidambaram Stadium in Chepauk, built around 1977. This Chidambaram Stadium had a serious problem with respect to corrosion, and we have to identify which of the beams had corrosion problem in order to remove those beams and repair the stadium so that the other portion which was all right could be made use of. You can see one of the reasons why in such a place you have failure is because of the lack of maintenance. Here you can see the rainwater stagnating, passing through the gallery and causing an unsurmountable amount of corrosion at the bottom. You can see the effect of that ponding of rainwater has caused the bars to corrode here, and the entire gallery had to be changed. And one interesting point which we could see in the Chidambaram Stadium was it was preferential corrosion between main bar and stirrups. Stirrups always got corroded first because it is closest to the outside atmosphere. When the stirrups are reduced in its diameter, still the main bar has got adequate capacity. Therefore, the type of failure in those bars shifts from flexural failure to shear failure. So, because the beam is susceptible for shear failure, the failure happens without any warning. Therefore, the corrosion of steel changes the pattern of failure, which the designer has envisaged in his design equations. Another interesting failure which I would like to present to you is at a place called Tuticorin. It is in Tuticorin thermal plant. Here, lot of electrical conduits are taken. When we examined, various tunnels has been provided for carrying coal to in the thermal plant. Wherever they had provided electrical conduits, and when the electrical conduits was not treated properly, the reinforcement inside the slab in the gallery had been corroded due to electrochemical action. Here you can see the corrosion of steel and the conduits going. Whenever the electrical conduit is operated with either switching on or switching off, the flux seems to affect the reinforcement, and therefore some type of protection had to be given for the reinforcement from corrosion, especially in areas where electrical activity is high. This is another place again in Tuticorin, where architectural facade has encouraged corrosion to take place. So architecture should match the corrosion requirement. Otherwise, architecture itself can become a cause for corrosion, as indicated in this slide. I want to present to you one case study of a Hong Kong bank building. This Hong Kong bank building was built by Robert Light when he was during the 1780s. This building is a 4-story building owned by Hong Kong Bank. The question came with upgradation of the banking system. They wanted to increase the load carrying capacity of the floors. The floors in those days was made with the jack arch floor. The floors were designed for 200 kg per square meter, whereas now the bankers wanted to use it for 350 to 400 kg per square meter. The option is demolish this building and rebuild. The second option is retrofit the building for increased load so that demolition is avoided. We suggested retrofitting, and I'm going to show you some methods by which we qualified the structure after the structure had been retrofitted. This is the building, 4-story building, just opposite to Port Trust. You can see the beautiful architectural features of this building. Nobody would like to demolish the building with such architectural beauty. Now, this is the jack arch floor. These are the steel girders. This is the arch. So we did loading in order to find out whether the jack arch floor was capable of carrying the correct load. After retrofitting the jack arch floor with the introduction of additional strengthening, we loaded the structure. This is the plaque of that building. This is how we loaded the structure. On each and every floor, we marked the loading area, and we loaded it with the steel ingots up to 400 kg per square meter. And when we loaded, we measured the deflection of the beams, deflection of the jack arch floor, and showed that the deflection of the jack arch floor was negligible. Deflection of the beam was within code prescribed limit for serviceability of the building, and hence the building was loaded for 1.25 times the live load with steel ingots. in steps of 25 kg per square meter, and the load deflection curve showed excellent performance, linear performance, and hence the building was qualified and the building has been put back to service. This repair was done in 1990, and till today the building is serving the Hong Kong Bank excellently well without any difficulty. So full-scale testing is possible, and full-scale testing will reveal the condition of the building, especially in case where you don't have reinforced concrete, but you have a composite system as in this case, that is steel girder, jack arch roof, and infill walls. This is how we measured the deflection. You can see the deflectometers are placed here. This is a steel girder, this is the jack arch. So, another very interesting failure which I would like to discuss with you is that which belongs to MIL Industries. The MIL Industries is Tuticorin based. They their industry is for cultivating prawns in ponds near the Tuticorin seashore. So seawater has to be pumped into the pond for growing the prawns. So because it is seawater, you need intake tower in the sea, and from the intake tower, you also need aqueduct to carry the seawater to the pond. This is the intake tower. This is Bay of Bengal. In Bay of Bengal, you have the intake tower. This is the conduit, reinforced concrete conduit through which you carry the seawater, and these are the entire structure is standing on piles, and unfortunately, because it is seawater, it is susceptible for very heavy corrosion. Now, unfortunately, all warnings given regarding the corrosion were not heeded, because they could not stop pumping water to the pond, because unless pumping water is done, the prawn culture cannot be made. So harvesting is done once in 6 months, and in 6 months you can in between you cannot do very costly repair work. So they proceeded without strengthening or protecting the steel. You can see the corrosion effect. You can see the corrosion here on the steel tubes. It's a pile foundation. You can also see the effect of corrosion here. This is how it failed. Now, on one fine day, 6 spans failed due to reinforcement giving away in the aqueduct. So what you see here is the collapsed portion of the aqueduct. This is how it has collapsed. This is the overall view of, this is the existing structure. This is the existing structure. This is how it has collapsed. Now the question is to rehabilitate it. They wanted rehabilitation to be done and the water to be restored within a week, because within a week they have to change the water. So we put a barrier here, put a barrier here, put a hume pipe between these two barriers, and water was pumped back so that the prawns don't die in the pond. And after 6 months, the entire bridge was removed and a new bridge was constructed. We will see some of the multi-story building flats. Many of the multi-story building flats are overloaded due to non-compliance with respect to codal provision. I would like to show one instance of a multi-story building, how the failure has occurred and what type of support we from the university gave in order to see that the building is the building doesn't collapse. You can see most of the buildings have a configuration like this. If you have a configuration like this, you have all the columns aligned in one direction. If you see XX direction, but if you see YY direction, the frames are not aligned. Therefore, the building has got reentrant corners, the building has got diaphragm discontinuity, and the building has got columns which are misaligned if you try to figure out how the load will get distributed in the YY direction. So most of the buildings have this type of configuration where you have a column which comes and sits on a cantilever, and this cantilever supports the bottom story is a car park, and because it's a car park, it is a stilt floor. So you have floating column, you have increased height of ground story, and you have a soft story. Discontinuous vertical members, you have discontinuous vertical members. These are the normal type of discontinuities you have in the existing flats. Moment resisting frames are not well defined. Beams are eccentric with column lines. Beams not framed into elevator core walls. Beams are not framing into the lift core. And the detailing is done poorly. You have at the plastic hinge, you have the lap joint. At the plastic hinge, you have the lap joint. This is again another problem. How do you retrofit these buildings? These are areas where the red lines come, that which does not follow the code of practice. Deficiencies in the analysis and design. These are mostly designed for gravity loads only, designed for lower seismic force. Neglect of stiffness from masonry infill is usually witnessed. Unaccounted addition and alteration, and nowhere P delta effect has been considered in the analysis and design. The strategies that we have suggested in about half a dozen flat systems is global retrofit strategies. Two strategies can be proposed. One global retrofit strategy, another local retrofit strategy. Local retrofit strategy is strengthening the beams and columns, but that will not give you a solution for problems like misaligned columns, which demand a global retrofit strategy. Increasing the lateral strength and stiffness by means of addition of infill walls, shear walls, frames, and braces. Reduction of irregularities, reduction of mass. These are the global retrofit strategies. You can see in this particular case, we have used an infill wall to strengthen the soft story and strengthen the foundation by means of addition to the foundation. By doing this, we were able to show that the building now is amenable to code prescribed limits, and therefore many of the buildings were provided with such intervention. Another alternative was to go in for a shear wall in the base in the open story. For the purpose of allowing opening, you can have wing walls instead of a full shear wall. Again, this will increase the lateral load carrying capacity of the ground floor. This solution, addition of buttress wall, we used for a 10-story building belonging to Tamil Nadu Electricity Board. The Tamil Nadu Electricity Board had built a building housing their main office in Anna Salai, a third-story building. But that was designed in 1970s and 80s, which did not have adequate seismic protection. In order to have the seismic protection, we have introduced buttress walls on either side, separate foundation for the buttress wall on either side, so that the seismic load is carried by the buttress walls that we have now introduced, and the inner portion of the building, which houses the offices, is not changed at all. This is an overall global retrofit strategy which we used for a 10-story building. Now, in some cases, you can also go, this is possible in industrial structure. In industrial structure, you can go for what is known as bracing the open ground story, which will again increase the lateral load capacity. Many times, the existing structure has to be drilled and damaged. So we have evolved a method by which the existing structure is not touched at all, but at the same time, the bracing can be introduced by using suitable fabrication system. The fabrication system that you can use without any intervention on the existing structure, but still will give the additional lateral load capacity is shown in this slide. In many cases, careful overloading of the structure has initiated the failure. Design should be followed meticulously. Overloading the structure may cause collapse. The example of an apartment building shows how a failure can occur. We have seen an apartment building. You can see this is this was designed as a 6-story building. They built the 7th story. They built the 8th story. It was designed only for 6 stories. When they built the 8th story, the bottom story column lateral literally burst. And when it burst, people are living in the upper floors. So temporarily, the building had to be supported in order that it doesn't collapse. The support that we could muster at the time when the failure had occurred is what I have shown here, is supported by jacks. Of course, the load was completely relieved, and after this, detailed analysis, design, court case, everything was taken, and ultimately the building was saved by removing 2 floors, by deloading the structure, so that the structure now is safe. At the same time, it has got also the lateral load resistance. For increase in lateral load resistance, column sizes were increased. For increase in the vertical load carrying capacity, adequate reinforcement was designed. This is how temporary supports supported the building. This is how deloading occurred. The 2 stories were removed. 8th story became again 6th story. Thank you very much. I tried to give you an overview of different failure of structures and the methods that you can use to retrofit them. Thank you.
Thank you so much, sir. The forum is open for questionnaire session.
Good afternoon, sir.
Yes.
Sir, I'm Dr. Guru Prasad from Bangalore, sir. Namaste. Sir, regarding the retrofitting of older structures, sir, when we come to this, especially when people want to go for an additional floor in a building, maybe if it's just a residential building itself, but the building is nearly close to 50+ years old. In such cases, we are going to carry out this non-destructive testing, especially to assess what is a particular grade of concrete which has gone into the columns, maybe it's 50-year-old column, and the walls which have been provided, especially are around 1 feet thick walls. So that is in the older buildings, as we know, in many parts of our country, we go for the larger wall thickness. In such cases, what would be the critical points which we need to consider in going for an additional floor in such buildings, sir?
Yeah. First of all, one has to do what is known as condition assessment.
Yes.
Condition assessment, we should know the type of structure. Is it a framed structure or is it a bearing wall building? Should be assessed. If it is a bearing wall building, and if you are putting one more story, you are limited by the bearing capacity of the walls that you have.
Okay.
If the bearing, if you want to increase the bearing capacity of the walls that you have, you can increase it by what is known as a split and bandage technique, in which the walls are chased out up to a quarter times width of the wall, and in the chased out portion, you can introduce new reinforced concrete bands.
Okay.
These reinforced concrete bands will have to be introduced at selected levels. For instance, it is introduced between the lintel level and the roof level, right round the building.
Okay.
If you introduce such a band, that band will contain the brick masonry, and it will also give additional seismic resistance, because it will behave as a belt for your entire structure. Now, in addition to this, you might also have to check the foundation.
Yes.
The foundation can be strengthened. The foundation can be strengthened. First of all, we should know what is the existing foundation.
Yes.
After knowing what is the existing foundation, there is a technique known as needle beam technique.
Okay.
Below the plinth beam, you introduce a transverse beam by having an opening in the brick masonry wall. The transverse beam will be perpendicular to the existing plinth beam, but it will be below the existing plinth beam.
Okay.
And this beam will have to be supported by two piles, one at about 4 feet interval from the face of the wall, and the next one at 8 feet interval. So this piles will carry the load. The building will, your extra floor load will come on the plinth beam, and the plinth beam will transfer the load on to the needle beam. The needle beam will transfer the load to the piles that you have placed. That is the system of load transfer that you will have to work out for a multi-story building.
Okay, sir.
It's going to be a building which is say 2-story, 3-story, 4-story. You will be able to get away with ground improvement technique. If it is clay soil, if you inject lime, your bearing capacity is likely to increase.
Okay, sir.
By about 10 to 20%. So if your load requirement is not very high, you can go based on ground improvement. If your load requirement is very high, you go with additional structural modification.
Okay, like inclusive of any additional bands in between the.
Yeah. Suppose you want to also give seismic protection.
Okay.
You can give bands both in the vertical direction as well as in the horizontal direction. Vertical direction on either side of the openings, window and door opening.
Okay.
And horizontal direction between plinth and sill, and between lintel and roof.
Okay. Okay, sir.
Horizontal bands.
Sir, but the thing is that in some buildings, what I've come across, they are pretty old. There is side stone masonry as a footing where they have gone up to 4 courses.
Yeah.
And they want to go for with the what they already have the sanction plan where they have an additional floor above. After I've taken a few test bits of the particular to check the foundation, what is the type of foundation, I've seen around 4 courses of side stone masonry. And they still want to go with another floor on top where the wall thickness is around 1 feet, but they are pretty old buildings, sir.
Yeah.
I've checked a few in Madras as well as in Bangalore here. Cases, I do see that to touch those walls, as you said, so to provide the bands in between, I feel a little thoughtful about to disturb the walls because they are also some of them built with lime mortar and some of them with earthen mortar also. As you know, in the olden days.
Actually, it may not be necessary to chase out and introduce the band inside. If your wall is weak,
yes,
you
sir,
introduce the bands on the wall, on both sides.
Okay, sir.
Stitch them through reinforcement going from one band to the other band. Internal band and external band.
Okay, sir.
And you can be stitched, but the wall itself will not be touched.
Fine, fine. Thank you very much, sir. Actually, I had met you long ago at IIT Madras through Professor Muthu, sir, at IIT Madras.
Okay.
So it is a great pleasure again talking to you, sir. Thank you very much.
Thank you.
Very nice presentation, sir. Thank you.
Thank you.
Sir, good afternoon, sir.
Yes.
Myself, Sairam from Vellore Institute of Technology.
Yeah, yeah.
Sir, actually, you told whatever the Maunivakam building, whatever the things you have told for the building which is collapsed.
Yeah.
For the other building, you have not told anything, sir. Observations.
Yeah. See, the building that has collapsed, the defects that I have shown are all the defects that are there in the building that has collapsed. The building that was standing had cracks, and when the cracks were examined, we could identify that almost all problems which were in the buildings that had collapsed also existed in the building that was still standing. For instance, there was no development length for the bar from the beam to the column. The lapping has been provided at the same section, and then the beam span was too high. The alignment of the column below the basement and above the basement was not okay. All these problems existed. And in addition to the existing problems, the structure had also had cracks. So when they asked us, the committee, whether it is possible to retrofit, we said it is possible to retrofit, but retrofitting will also mean people working, and when the people are working, their safety is also under peril. Therefore, either you retrofit by temporarily supporting the entire structure or go in for a new building. Ultimately, the government preferred to go in for a new building.
Sir, but no retrofitting has done for the existing building, sir?
No, the existing building was pulled down.
Okay, sir.
And
sir,
a new building was put up there.
Okay,
sir. The methods that we suggested for retrofitting the existing building were not followed because they felt for retrofitting, it also involves risk for the workmen.
Yes, correct, sir. Sir, any detailed report will be available in the net, sir, for this?
Yeah, detailed report is available.
Okay, sir. Okay, thank you, sir.
Any other question?
No, sir. Thank you, sir. Thank you very much, sir.
Okay. It's nice talking to you.
Yes, sir.
Thank you, sir. Thank you for a spectacular presentation. Thank you for sharing a detailed explanation and inference on each structural member failure, on construction errors and remedy. Thank you very much, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you very much.
Thank you.
Thank you so much, sir. Thank you, sir. Thank you, sir.
The feedback form is posted in the chat box. So kindly fill the feedback form to receive the certificates. You will be receiving the certificates in 7 working days. Now I request our convener, Dr. Rajkumar sir, to propose the vote of thanks.
Thank you, Patra Madam. Good afternoon to all. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. First and foremost, I express my gratitude and thank all our invited speakers, Dr. A. Santakumar sir, Dr.N.Subramanian sir, Dr.V.Rajendran sir, and Er.Dhruvesh sir, who, despite their busy schedule, has found time to grace this occasion by delivering a wonderful lecture. The presentations have given deep insights into the case studies on failure, repair, and rehabilitation structures and reveal some interesting facts. I must mention a deep sense of appreciation for Dr. N.Subramanian, sharing her experience on different types of failures and repairs with practical examples. Further, we're grateful to Dr. V.Rajendran for sharing the valuable information on his experience in repairing the existing underwater structure in Lakshadweep. I'd like to express my sincere thanks to Er.Dhruvesh Shah for sharing his knowledge on case studies on failures, repair, rehabilitation, and mostly on corrosion protection systems of structures. My sincere thanks to Dr. A. Santakumar sir for sharing his information on Molyoka building collapse and other case studies. I'd like to thank Chairperson Dr. Radhakrishnan Pillai and other Executive Council members from ICA, Chennai Centre for supporting this program. I'd like to convey my sincere thanks to Dr. P.T. Ravichandran sir, HOD Civil Engineering, and the management of SRM ISG for supporting this program. We are really grateful as well as obliged to thank the sponsors, UltraTech Cement Limited, for extending their support in the form of sponsorship. For everything you have done for us in the past, everything you still do and will continue to do, we at ICA Chennai Centre just want you to thankful how we are, and we look forward to a prosperous future together. Last but not least, I extend my heartfelt thanks to Ms. Ramya, manager from ICA Chennai Centre, for hard work in conducting this webinar and who participated only and making the webinar even full. Thank you.